Right now, in the darkness above your head, something is rotating. You cannot see it. You cannot hear it. But it is there, spinning at velocities that would shred your body into atomic vapor in less than 1 second. This object is not a storm. It is not a planet. It is a galaxy. And the structure you think you know, the elegant spiral you've seen in every astronomy textbook, is a lie. What actually exists in the cosmic void is far stranger, far more violent, and far more terrifying than anything you were taught to believe. The Milky Way, the system you call home, is classified as a barred spiral galaxy. Scientists have been using this term for over a century, categorizing cosmic structures into neat boxes with clean definitions. Spiral, elliptical, irregular, lenticular. These words create the illusion of understanding. They suggest that we have mapped the universe's architecture and decoded its fundamental forms. But recent observations from instruments like the James Webb Space Telescope and the Hubble Space Telescope have revealed something that shatters this comfortable taxonomy. The categories we created are not just incomplete, they are fundamentally wrong. Galaxies do not fit into our classification system because galaxies were never designed to be understood by human minds. Every galaxy you have ever seen in a photograph is a frozen moment in a process of transformation so violent and so prolonged that it operates on timescales your consciousness cannot process. What appears stable is actually mid-catastrophe. What looks organized is actually chaos, compressed by gravity into temporary patterns. And what we call different types are not separate species of cosmic object. They are crime scenes at different stages of investigation. Each classification reveals a different method of destruction, a different failure mode in the universe's attempt to organize matter against the void. The problem begins with observation itself. When you look at a galaxy, you are not seeing a static structure. You are seeing light that left that system millions or billions of years ago, traveling across distances so vast that the galaxy you observe no longer exists in that form. By the time photons reach your eye or reach our telescopes, the object that emitted them has already transformed. It has collided with neighbors. It has consumed smaller systems. It has been stripped by tidal forces or ignited in bursts of star formation that changed its fundamental character. You are looking at ghosts, and the ghosts are lying to you about what they were and what they have become. Scientists classify galaxies based on morphology, the shapes we can observe from our position in space. But shape is the least important property of these systems. It is like classifying humans by their silhouettes and assuming you understand their internal biology, their thoughts, their capacity for violence. The classification system we use was developed by Edwin Hubble in 1926, nearly a century ago, when our instruments could barely resolve the structure of nearby galaxies. We have been building on this foundation ever since, adding categories and subcategories as new observations reveal anomalies that do not fit. But we have never stopped to ask the fundamental question: what if galaxies are not meant to be classified? What if their diversity is not a spectrum of types, but a warning about the instability of cosmic structure itself? This script will expose the types of galaxies you never knew existed, not because they are rare or difficult to observe, but because acknowledging their existence forces us to confront how little we actually understand about the universe we inhabit. You will learn about spiral galaxies that are not actually spiraling, about elliptical galaxies that are not ellipses, about irregular galaxies that follow hidden rules we cannot detect. You will discover ring galaxies that should not be possible under known physics, dwarf galaxies that behave like predators, and dark galaxies that are essentially invisible. Each type represents a failure of our models, a crack in our understanding, and a glimpse into cosmic mechanisms that operate according to principles we have not yet discovered. Prepare yourselves. The comfortable universe you thought you knew is about to collapse. And what replaces it is far more strange and far more hostile than you ever imagined. Look at the Hubble tuning fork diagram. You have probably seen it before. A neat flowchart showing galaxy evolution from left to right, ellipticals on one prong, spirals on the other, converging at a single point labeled S0. This diagram appears in every introductory astronomy textbook published in the last 90 years. It hangs on the walls of planetariums. It is taught to children as cosmic truth, and it is completely catastrophically wrong. Edwin Hubble created this classification system in 1926, the same year Schrödinger published his wave equation, and the same year Robert Goddard launched the first liquid-fueled rocket. Hubble was working at the Mount Wilson Observatory with the 100-inch Hooker telescope, the largest instrument in the world at that time. He photographed 46 galaxies and noticed they fell into recognizable patterns. Some appeared round and smooth. Others showed spiral structure. A few looked chaotic and formless. He organized them into categories and drew a diagram suggesting evolutionary relationships. The diagram became canon, and canon became prism. The tuning fork divides galaxies into three main families. Ellipticals, labeled E with numbers 0 through 7 indicating how elongated they appear. Spirals, labeled S or SB, depending on whether they possess a central bar, with subcategories A, B, and C based on how tightly wound their arms are. And irregulars, labeled IRR, a catch-all category for everything that does not fit the other boxes. This system is simple. It is memorable. And it is based on a fundamental misunderstanding of what galaxies actually are. Hubble believed the tuning fork represented an evolutionary sequence. He thought elliptical galaxies were young objects that would eventually develop spiral arms as they aged, or that spirals would lose their structure and become ellipticals. The diagram suggests progression, development, a life cycle that mirrors biological evolution. But galaxies do not evolve like organisms. They do not mature from youth to old age, following a predetermined path. They collide. They merge. They are torn apart by tidal forces and reassemble through gravitational collapse. The history of any individual galaxy is not a smooth trajectory, but a series of violent catastrophes separated by periods of relative stability. Modern observations have revealed that Hubble's evolutionary interpretation is backwards. Elliptical galaxies are not young systems waiting to develop structure. They are the end products of galaxy mergers, the cosmic graveyards where two or more spiral galaxies have collided and destroyed each other's organized structure. The smooth appearance of an elliptical is not pristine youth, but traumatic scar tissue. These systems have been through hell, and their featureless morphology is what remains when all internal structure has been erased by violence. The Hubble classification also assumes that what we see is what exists. But galaxies are three-dimensional objects observed from a single angle. A spiral galaxy viewed face-on looks completely different from the same galaxy viewed edge-on. From certain perspectives, a barred spiral can appear to have no bar at all. An elongated elliptical might actually be a spiral seen from the side. We are classifying objects based on their two-dimensional projections, like trying to understand the shape of a building by looking at its shadow. The shadow changes depending on the angle of light. The classification changes depending on our viewing angle. And we have no way to rotate the galaxy to see it from all sides. Then there is the problem of time. Galaxies change on timescales of hundreds of millions of years. A spiral galaxy undergoing a merger might spend 100 million years looking irregular and chaotic before settling into a new elliptical form. If we observe it during that transition phase, we classify it as irregular. But irregular is not a type, it is a temporary state. It is like classifying humans into categories and having one category called bleeding because you happen to observe some people while they were injured. The injury is not a permanent condition, it is a moment in a process. But our classification system treats momentary states as if they were eternal essences. The system also fails to account for internal dynamics. A galaxy classified as an elliptical based on its smooth external appearance might be hiding significant internal structure. Recent observations with advanced instruments reveal that many ellipticals contain rotating disks of gas and dust, embedded spiral patterns, or multiple kinematically distinct components that betray their merger origins. These features are invisible in optical photographs but become obvious when you measure velocity fields or observe in different wavelengths. The galaxy we called simple is actually a composite of multiple destroyed systems. each leaving behind kinematic fossils that preserve the memory of their independent existence. The Hubble system is also fundamentally biased toward large, bright galaxies. It was developed by observing the most massive and luminous systems that Hubble could detect with 1920s technology. But we now know that the universe is dominated by dwarf galaxies, systems containing only millions or billions of stars compared to the hundreds of billions in massive spirals. These dwarfs do not fit neatly into the tuning fork. Some show spiral structure despite their small size. Others look elliptical but have completely different formation histories than giant ellipticals. Still others are so diffuse that they barely qualify as bound structures at all. The classification system ignores the majority of galaxies in the universe because they were below the detection threshold when the system was created. Modern surveys with instruments like the Sloan Digital Sky Survey and the Dark Energy Survey have cataloged millions of galaxies across vast volumes of space. When astronomers try to classify this enormous population using the Hubble system, they find that roughly 20 to 30% of observed galaxies do not fit into any standard category. These are not rare exceptions. They are a significant fraction of the total population. A classification system that fails to accommodate 1/3 of observed objects is not a useful tool. It is an obstacle to understanding. The problem becomes even more severe when you observe galaxies in the early universe. The James Webb Space Telescope is now detecting galaxies that formed less than 1 billion years after the Big Bang, systems existing when the universe was only 7% of its current age. These galaxies look nothing like the mature spirals and ellipticals in the nearby universe. They are clumpy, irregular, often showing multiple bright knots of star formation rather than organized structure. Some appear to be in the process of assembling from smaller fragments. Others show morphologies that have no analog in the local universe. The Hubble classification system, built on observations of nearby mature galaxies, is utterly useless for describing these early systems. Astronomers have tried to patch the system by adding new categories. S0 galaxies, lenticulars that are neither elliptical nor spiral, peculiar galaxies, marked with a lowercase p, dwarf spheroidals, dwarf ellipticals, dwarf irregulars, ultra-compact dwarfs, blue compact dwarfs, ring galaxies, polar ring galaxies, shell galaxies. Each new category is an admission that the original system was inadequate. But rather than abandoning the framework, astronomers keep adding exceptions and subcategories, creating a taxonomic nightmare that is more baroque than informative. The fundamental error is assuming that galaxies are static types rather than dynamic processes. A galaxy is not a thing. It is an event. It is gravity organizing matter into temporary structures that exist for billions of years but will eventually be torn apart by cosmic expansion, consumed by mergers, or stripped by environmental effects. Classifying a galaxy is like trying to classify a cloud based on its shape. You can describe what it looks like at the moment of observation, but that description tells you nothing about the physical processes creating the shape or how the cloud will evolve in the next hour. What we need is not a better classification system, but a process-based understanding that describes galaxies by their formation history, their current dynamical state, and their evolutionary trajectory. Instead of asking what type of galaxy is this, we should be asking, what happened to this system? What is happening now? What will happen next? The shape is just a clue. The real story is written in velocity fields, chemical abundances, stellar populations, and dark matter distributions. These are the forensic details that reveal the truth. And the truth is that every galaxy is unique. Every system has experienced a different sequence of events, and no classification system can capture the full complexity of these cosmic catastrophes. But we cling to the Hubble tuning fork because it provides comfort. It suggests order in chaos. It tells us that we understand the universe's architecture and can organize it into manageable categories. This is a lie we tell ourselves to avoid confronting the terrifying reality that the cosmos is far more complex, far more violent, and far more resistant to human categorization than we want to believe. The Milky Way is a spiral galaxy. You have heard this fact your entire life. You have seen images of elegant spiral arms sweeping through space, glowing with blue stars and pink nebulae. The structure appears obvious. Stars orbit the galactic center in circular paths, and because they orbit at different speeds depending on their distance from the center, they get stretched out into spiral patterns. This is what you were told. This is what appears in every simplified explanation of galactic structure. And this explanation is completely fundamentally wrong. The problem is called the winding problem, and it was first identified in the 1960s by astronomers studying galactic rotation curves. If spiral arms were simply trails of stars being pulled into curved paths by differential rotation, they would wind up like thread around a spool. The inner regions of a galaxy rotate faster than the outer regions, completing one orbit in tens of millions of years compared to hundreds of millions of years at the edges. After just a few rotations, the spiral arms would become so tightly wound that they would disappear into smooth rings. The Milky Way has completed approximately 20 to 25 full rotations since its formation. By now, any spiral structure created by differential rotation should have been wound up beyond recognition billions of years ago. But spiral arms persist. They exist in galaxies throughout the universe, from young systems forming in the early cosmos to ancient galaxies that have existed for over 10 billion years. The structure is stable across timescales that should have destroyed it dozens of times over. This means that spiral arms cannot be made of stars being dragged into curved paths. They must be something else entirely, something that maintains its pattern even as individual stars move through it. Something that operates according to principles more subtle and more strange than simple orbital mechanics. The solution is density wave theory, proposed by C.C. Lin and Frank Hsu in 1964. Spiral arms are not collections of stars moving together. They are patterns of compression propagating through the galactic disk, like sound waves moving through air. The stars themselves orbit the galactic center in roughly circular paths, but as they move, they encounter regions of higher density where gravity is slightly stronger. These density enhancements slow the stars down temporarily, causing them to bunch together. The bunching increases the local gravitational field, which attracts more stars, reinforcing the pattern. The result is a spiral-shaped traffic jam that rotates through the galaxy independently of the stars themselves. Think of it this way. Imagine cars driving on a circular highway. If there is an accident in one section, traffic slows down and cars bunch together. The traffic jam appears as a concentrated cluster of vehicles that persists even as individual cars slowly move through it, accelerating once they pass the bottleneck and leaving the jam behind. The jam itself rotates around the highway more slowly than the cars, creating a persistent pattern that is not made of any particular set of vehicles. Spiral arms work exactly like this. They are gravitational traffic jams. The stars you see glowing in the spiral arms are not permanent residents. They're temporary visitors passing through a region of enhanced density. But this explanation creates new problems. Density waves should dissipate over time due to friction and gravitational interactions. The wave pattern should gradually lose energy and smooth out, just as sound waves in air eventually fade to silence. Some mechanism must be continuously regenerating the spiral pattern, pumping energy into the density wave to prevent it from decaying. Astronomers have proposed several candidates for this mechanism. Gravitational interactions with satellite galaxies orbiting the main system could periodically perturb the disk and regenerate spiral structure. Bars of stars forming in the galactic center could act as rotating gravity wells that drive spiral patterns in the surrounding disk. Turbulence in the interstellar medium could create density fluctuations that organize into large-scale patterns through self-gravity. None of these explanations is completely satisfactory. Each requires special conditions or fine-tuned parameters that may not exist in all spiral galaxies. And yet, spiral structure is common, appearing in roughly 60% of massive disk galaxies in the nearby universe. Whatever mechanism maintains spiral arms must be robust in general, not a fragile arrangement that only works under rare circumstances. This suggests we are still missing something fundamental about how these structures form and persist. Recent observations with instruments like the Atacama Large Millimeter Array have revealed additional complexity in spiral arm structure. The arms are not smooth, continuous features but are broken into segments, spurs, and feathered edges that connect to the main spiral pattern at various angles. These substructures suggest that multiple physical processes are operating simultaneously, each creating patterns at different scales. Gravitational instabilities in the gas disk create small-scale structure. Density waves organize material on large scales. Stellar feedback from supernovae and stellar winds disrupts local regions and injects energy that can drive turbulence. The spiral pattern you see in a photograph is the combined result of all these processes operating simultaneously, creating an appearance of organization that conceals underlying chaos. The situation becomes even stranger when you examine what is actually glowing in spiral arms. The bright blue stars that trace the spiral pattern are young, massive stars with lifetimes of only 10 to 100 million years. These stars are born in the spiral arms and die before they can complete even one full orbit of the galaxy. They are marking the locations of recent star formation, regions where dense molecular clouds have been compressed by the density wave and triggered to collapse. But the density wave itself is made primarily of older, redder stars that are far less luminous and therefore invisible in most photographs. What you see when you look at a spiral galaxy is not the actual structure but only the most recent star formation activity. This creates a disturbing realization. The spiral arms you observe are ghosts. They are the fluorescent corpses of collapsed gas clouds, glowing briefly with the light of young stars before those stars exhaust their fuel and fade. The actual gravitational structure creating the pattern is invisible, composed of dark matter and dim older stars that provide the mass but produce almost no light. You are seeing the effect but not the cause. The pattern is real, but the mechanism is hidden. And what is hidden might be operating according to principles we do not yet understand. Some spiral galaxies show grand design structure, with two prominent spiral arms that can be traced smoothly from the galactic center to the outer edges. The Milky Way, Andromeda, and the Whirlpool Galaxy all display this morphology. But other spirals show flocculent structure, with multiple fragmented arm segments that give the galaxy a fluffy, cotton-like appearance. The difference between grand design and flocculent spirals is not well understood. Grand design systems tend to have companion galaxies, or strong central bars that could drive organized density waves. Flocculent spirals lack these features and may be experiencing stochastic star formation driven by local gravitational instabilities rather than global spiral patterns. But even this distinction breaks down when you examine individual systems. Some galaxies show grand design structure in their inner regions and flocculent structure in their outer disks. Others show the opposite pattern. Then there are spiral galaxies that should not exist at all, ultra-thin spirals with disk thickness less than 1/10 their diameter, creating structures so fragile that they should be torn apart by internal gravitational instabilities. Spiral galaxies with asymmetric arms, where one arm is brighter or more extended than the others, violating the symmetry that density wave theory predicts. Spiral galaxies in dense cluster environments where tidal interactions with neighbors should have destroyed their delicate disk structure long ago. Each of these anomalies suggests that our understanding of spiral formation is incomplete. The bars that appear in roughly 2/3 of spiral galaxies add another layer of mystery. These elongated structures extending from the galactic nucleus rotate as solid bodies, defying the differential rotation that dominates the rest of the disk. The bar's existence requires a specific distribution of stellar orbits that organize into an elongated pattern and maintain that configuration for billions of years. Small perturbations should cause the bar to dissolve or to grow until it consumes the entire disk. Bars persist with stable lengths and axial ratios across cosmic time. The Milky Way's bar is approximately 27,000 light-years long and has probably existed for billions of years. How it formed and why it remains stable are open questions that theoretical models struggle to explain. Bars also affect the spiral structure they host. Barred spirals tend to have two prominent arms that originate at the ends of the bar and sweep back in trailing patterns. Non-barred spirals can have multiple arms emerging from the nucleus at various angles. The connection between the bar and the spiral pattern suggests they are dynamically linked. with the bar acting as a driver that generates and maintains the spiral density wave. But the exact mechanism is unclear. Some models propose that the bar's gravitational potential creates resonances at specific radii, where orbital frequencies match the bar's rotation rate, and these resonances organize the spiral pattern. Other models suggest that the bar channels gas inward toward the galactic center, increasing the gas density and triggering star formation that creates spiral arm features. The rotation curves of spiral galaxies reveal the most disturbing secret of all. When astronomers measure how fast stars orbit at different distances from the galactic center, they find that orbital velocity remains roughly constant from the inner disk all the way to the outer edges and beyond. This is completely wrong according to Newtonian gravity. In a system like the solar system, where most of the mass is concentrated at the center, orbital velocity decreases with distance following Kepler's laws. But galaxies do not behave this way. Their flat rotation curves indicate that mass is distributed throughout the disk and extends far beyond the visible stars into a vast dark matter halo. This dark matter provides the gravitational field that keeps the outer stars orbiting faster than they should based on visible matter alone. The spiral arms you see are therefore floating in an invisible ocean of dark matter that provides most of the galaxy's mass and determines its overall gravitational structure. The visible spiral pattern is just foam on the surface of a dark sea. What lies beneath, the actual distribution and nature of the dark matter, remains unknown. We can infer its presence from gravitational effects, but we cannot observe it directly. It could be composed of exotic particles that interact only through gravity. It could be primordial black holes. It could be something we have not imagined. And it determines the behavior of spiral galaxies in ways we cannot predict because we do not know what it is. The term spiral galaxy is therefore deeply misleading. These systems are not spirals in any simple geometric sense. They are rotating disks of stars and gas embedded in dark matter halos, hosting transient density wave patterns that masquerade as stable structures, glowing primarily in regions of recent star formation that mark compressions in the underlying gravitational field. The spiral shape you see in photographs is a momentary snapshot of a continuously changing pattern, like a photograph of ocean waves that captures the shape of the water but tells you nothing about the currents, the temperature gradients, or the hidden depths below the surface. When you look at a spiral galaxy, you are seeing a lie. Not a deliberate deception, but a failure of human perception to grasp the true nature of what is being observed. The structure is real, the physics is real, but the interpretation, the comfortable label spiral galaxy, is a simplification so extreme that it borders on fiction. And if we are this wrong about the most common and most studied type of galaxy in the universe, what else are we wrong about? Elliptical galaxies appear smooth. They glow with a uniform reddish light that fades gradually from a bright core to dim outer regions. They show no spiral arms, no dust lanes, no bright blue stars marking recent star formation. They look peaceful, ancient, and dead. This appearance is not deceptive. Elliptical galaxies are cosmic graveyards. But what died to create them is far more violent and far more disturbing than you were ever told. The standard explanation describes ellipticals as old, evolved systems that have exhausted their gas supplies and ceased forming new stars. The red color comes from old, low-mass stars that have been burning for billions of years, outliving their more massive blue siblings. The smooth appearance reflects a lack of organized structure, with stars moving in random orbits rather than the orderly rotation seen in spiral disks. This description is technically accurate but profoundly incomplete. It tells you what ellipticals look like now, without explaining the catastrophic violence required to create them. Elliptical galaxies are the products of galaxy mergers. When two spiral galaxies collide, their ordered disk structures are destroyed through a process so violent that it erases all memory of the original spiral patterns. The collision does not happen quickly. Galaxies are mostly empty space, and when they interpenetrate, individual stars almost never collide because the distances between stars are vast compared to stellar diameters. But the gravitational fields interact immediately. Each galaxy feels the tidal forces from the other, stretching and distorting the stellar distributions. Stars are pulled from their original orbits and scattered into new trajectories. The disks warp, buckle, and eventually shred completely. Computer simulations of galaxy mergers reveal the full brutality of this process. When two spirals approach each other, they begin a complex gravitational dance that can last for over 1 billion years. On the first pass, tidal forces create long streams of stars called tidal tails that extend for hundreds of thousands of light years into intergalactic space. These tails are visible evidence of the violence occurring in the collision zone. The galaxies separate after their first encounter, but they are gravitationally bound and will return. On subsequent passes, the tidal interactions become stronger, more stars are stripped away. The gas disks collide, creating shock waves that heat the gas to millions of degrees and trigger intense bursts of star formation. The central regions spiral toward each other, losing energy through gravitational interactions until finally the two galactic cores merge into a single nucleus. What emerges from this collision is not a spiral galaxy. The organized rotation that defined both original systems has been thoroughly scrambled. Stars now move on elongated, randomly oriented orbits that create a three-dimensional distribution rather than a flat disk. The result is an elliptical galaxy, a system whose smooth appearance conceals its traumatic origin. Every elliptical you observe is the scar tissue of a violent collision, a memorial to the destruction of multiple spiral galaxies that no longer exist as independent entities. The evidence for this merger origin is everywhere once you know what to look for. Many ellipticals show faint shells, arc-like structures in their outer regions that are the remnants of tidally disrupted satellite galaxies. These shells are fossil tidal streams, the scattered remains of smaller systems that were consumed by the growing elliptical. Some ellipticals show kinematically distinct cores, central regions that rotate in the opposite direction from the main body. This counter-rotation is the signature of a previous merger where the incoming galaxy's angular momentum was opposite to the host's rotation, creating a persistent kinematic fossil that survives billions of years after the collision. Deep imaging reveals that many ellipticals are surrounded by extensive faint envelopes of stars stretching far beyond the bright central regions. These stellar halos are built from the accumulated debris of past mergers, the scattered remnants of destroyed galaxies that were incorporated into the growing system. The halo's existence proves that ellipticals continue to grow through ongoing accretion of smaller satellites, a process called galactic cannibalism that has been occurring throughout cosmic history. But not all ellipticals form through equal mass mergers. The largest elliptical galaxies, the supergiant systems found at the centers of massive galaxy clusters, grow through a different and more disturbing process. These monsters sit at the bottom of the cluster's gravitational potential well, the deepest point where gravity is strongest. Smaller galaxies orbit through the cluster, and as they pass near the central giant, dynamical friction slows them down. Dynamical friction occurs when a moving galaxy's gravitational field pulls on the surrounding cluster members, creating a drag force that gradually removes orbital energy. Over billions of years, this friction causes satellites to spiral inward and merge with the central galaxy. The result is called a brightest cluster galaxy, or BCG. These systems contain trillions of stars spread across diameters exceeding 1 million light-years. They are the largest single objects in the universe, assembled through the cannibalization of hundreds or thousands of smaller galaxies over 10 billion years of cosmic history. The BCG's enormous size is not evidence of special formation conditions. It is simply the inevitable result of living at the center of a crowded environment where everything eventually falls toward you and gets consumed. The supermassive black holes at the centers of elliptical galaxies carry their own record of merger violence. When two galaxies merge, their central black holes eventually sink toward the center of the merged system through dynamical friction. Once they get close enough, they form a binary black hole system that orbits while radiating gravitational waves. This radiation carries away orbital energy, causing the black holes to spiral closer together until they finally merge in a catastrophic collision that releases more energy in gravitational waves than all the stars in the visible universe emit in light during the same time interval. The merged black hole receives a gravitational recoil kick from the asymmetric emission of gravitational waves, potentially launching it out of the galactic nucleus at velocities exceeding 1,000 kilometers per second. Evidence for these recoiling black holes is mounting. Several elliptical galaxies show displaced cores, where the brightest part of the galaxy is offset from its center of mass by thousands of light-years. These offsets are consistent with recoil scenarios where a massive black hole merger kicked the surviving black hole out of the galactic center. The black hole is now wandering through the galaxy's outskirts, displaced from its natural position by the violence of its own formation process. Elliptical galaxies also reveal their traumatic history through their stellar populations. Spectroscopic observations show that many ellipticals contain two or more distinct populations of stars, with different ages, chemical compositions, and kinematic properties. One population might consist of old, metal-poor stars formed early in cosmic history. Another population might be younger and metal-rich, created during gas-rich mergers that triggered intense star formation. These multiple populations are archaeological evidence of multiple merger events, each adding new stars to the growing system and creating layers of stellar fossils that preserve the merger history. The most extreme ellipticals are called compact ellipticals, or relics. These systems have stellar densities exceeding those of normal ellipticals by factors of 10 or more, creating environments where stars are packed so tightly that gravitational interactions between them become significant. The origin of these compact systems is debated. They might be the stripped cores of larger galaxies that lost their outer envelopes through tidal interactions with more massive neighbors. Or they might be ancient galaxies that formed in the early universe when gas densities were higher, allowing stars to form in more compact configurations. Either way, their extreme properties make them laboratories for studying stellar dynamics under conditions that no longer exist anywhere else in the cosmos. Some elliptical galaxies show evidence of recent or ongoing gas accretion, despite having exhausted their internal gas supplies. This gas comes from the intergalactic medium, the hot diffuse plasma that fills the space between galaxies and clusters. As the elliptical moves through this medium, ram pressure can strip away hot gas from the cluster and funnel it toward the galaxy's center. If enough gas accumulates, it can cool and trigger new star formation, creating young blue stars that stand out dramatically against the old red stellar population. These rejuvenated ellipticals challenge the simple picture of ellipticals as dead systems, showing that gas accretion can temporarily restart star formation even in galaxies that have been quiescent for billions of years. The classification of elliptical galaxies by their apparent shape using the E0 through E7 system is another convenient fiction. An E0 galaxy appears perfectly circular on the sky, while an E7 appears highly elongated. But this classification confuses projection effects with intrinsic shape. An intrinsically spherical galaxy viewed from any angle appears circular. An intrinsically oblate spheroid, shaped like a flattened ball, appears circular when viewed along its rotation axis but elliptical when viewed from the side. An intrinsically triaxial ellipsoid with 3 different axis lengths appears different depending on which angle you observe it from. Without knowing the 3-dimensional shape and our viewing angle, the classification number tells you almost nothing about the galaxy's actual structure. Recent kinematic studies using integral field spectroscopy have revolutionized our understanding of elliptical galaxy structure. These observations measure the velocities of stars across the entire galaxy face, revealing how the system rotates and how much random motion exists in the stellar orbits. The results show that ellipticals are not a single family, but divide into 2 distinct classes. Fast rotators show significant rotation, with stars moving coherently around the galactic center. Slow rotators show little rotation, with stars moving primarily on random orbits. Fast rotators tend to be less massive and form through relatively gentle mergers that preserve some of the original angular momentum. Slow rotators tend to be more massive and form through violent equal mass mergers that completely scramble the angular momentum distribution. This division reveals that the term elliptical galaxy masks fundamental physical differences. A fast-rotating low-mass elliptical has more in common dynamically with a lenticular galaxy, a spiral that has lost its gas, than with a slow-rotating giant elliptical. The smooth appearance conceals structural diversity that only becomes apparent when you measure internal kinematics. Shape classification based on projected appearance is not just incomplete, it is actively misleading, grouping together objects that formed through completely different processes and have completely different internal structures. The reddest elliptical galaxies are called red and dead, systems where star formation ceased billions of years ago, and all remaining stars are old and dim. But even this designation is challenged by recent observations. X-ray imaging reveals that many ellipticals are surrounded by extended halos of hot gas at temperatures exceeding 10 million degrees. This gas is too hot to cool and form stars, but it is evidence of ongoing activity. Supernova explosions from the galaxy's remaining old stars inject energy into the gas, keeping it heated. The central supermassive black hole can also inject energy through jets of relativistic particles that heat the surrounding medium. These ellipticals are not dead. They are experiencing low-level activity that will continue for billions of years as the last stellar populations gradually age and expire. The future of elliptical galaxies is entropy. As stars age and die, they become white dwarfs, neutron stars, or black holes. These remnants produce no light and eventually fade from view. The galaxy becomes progressively darker as the remaining luminous stars exhaust their fuel. After 100 billion years, all stars capable of fusion will have died. The elliptical will consist entirely of stellar remnants moving through a sea of dark matter, invisible except through gravitational effects. After 1 trillion years, close gravitational encounters between stellar remnants will eject most of them from the galaxy into intergalactic space, leaving behind a sparse collection of brown dwarfs, white dwarfs, and black holes bound to the central supermassive black hole. The elliptical galaxy that looked smooth and peaceful in the present will become a dark tombstone, marking the location of what once was a brilliant stellar system. When you look at an elliptical galaxy, you are looking at death incarnate. Not the gentle fading of old age, but the violent aftermath of cosmic catastrophes that destroyed multiple spiral galaxies and scattered their stars into new configurations. The smooth appearance is not elegance, it is erasure. Every trace of the original structures has been removed by tidal forces and gravitational scattering. What remains is a collective memorial to destroyed worlds, a mass grave where billions of stars orbit in random confusion, forever separated from the organized structures they once inhabited. And this fate awaits every spiral galaxy in dense environments, including, eventually, our own Milky Way, which will merge with Andromeda in approximately 4 billion years, and create a new elliptical that will bear no memory of the spiral arms we see today. The term irregular galaxy sounds like a confession of ignorance. When Hubble constructed his classification system, he needed a category for galaxies that did not fit the neat patterns of spirals and ellipticals. So he created the irregular class, a taxonomic junk drawer where astronomers could dump everything that looked messy, asymmetric, or otherwise disobedient. The name suggests disorder, randomness, a lack of structure. This suggestion is false. Irregular galaxies are not chaotic. They are following rules we do not understand. The Large Magellanic Cloud and the Small Magellanic Cloud are the two most famous irregular galaxies, visible to the naked eye from the southern hemisphere as diffuse patches of light. They orbit the Milky Way as satellite galaxies, close enough that they have been known to human observers for thousands of years. Ancient Polynesian navigators used them for navigation across the Pacific Ocean. Arab astronomers documented them in the 10th century. But despite their familiarity, these systems defy classification. The Large Magellanic Cloud shows hints of a barred spiral structure, with a single prominent spiral arm extending from an elongated central bar. But the structure is lopsided, off-center, and fragmented. It does not look like any normal spiral galaxy. The Small Magellanic Cloud shows even less organization, appearing as a formless blob of stars and gas with no clear symmetry or defining features. Hubble classified both Magellanic Clouds as irregular galaxies, specifically as type IRRI, meaning irregular galaxies with some hint of resolution into bright stars in H2 regions where star formation is occurring. But this classification reveals nothing about why these galaxies look the way they do. It simply describes their appearance and moves on. The actual physics determining their morphology remained mysterious for decades after Hubble's death. Modern observations have revealed that the Magellanic Clouds are not primordially irregular. They have been deformed by tidal interactions with the Milky Way and with each other. As they orbit through the Milky Way's gravitational field, tidal forces stretch them, pulling stars and gas away from their centers and creating asymmetric distributions. The Magellanic Stream, a vast arc of neutral hydrogen gas extending over 100 degrees across the sky, is the stripped material torn from the Magellanic Clouds during their orbital passage. This stream contains roughly 200 million solar masses of gas, material that was once part of the clouds but has been gravitationally extracted and now trails behind them like blood from a wound. The irregular appearance of the Magellanic Clouds is therefore not intrinsic, but environmental. They would look different if they were isolated in intergalactic space, free from tidal disturbances. Their current morphology is a snapshot of systems being actively disrupted by gravitational forces from a more massive neighbor. In another billion years, they will look different again. The Milky Way will continue to strip material from them until eventually they are completely consumed, their stars and gas absorbed into the Milky Way's halo and disk. The irregular classification describes a temporary state, not a permanent type. This realization applies to irregular galaxies throughout the universe. Many irregulars show signs of tidal disturbances, asymmetric star formation patterns, or kinematic evidence of recent interactions. They are not naturally chaotic systems, but rather systems that have been perturbed by external forces. The irregular appearance is a response to environmental trauma, not an inherent property of the galaxy itself. But some irregular galaxies cannot be explained by tidal interactions. Dwarf irregulars, small systems containing only millions to billions of stars, often show asymmetric morphologies and patchy star formation, despite being isolated from massive neighbors. These systems lack the organized rotation seen in spiral disks and the smooth distribution seen in ellipticals. Their stars move on somewhat random orbits with significant velocity dispersion. Their gas is distributed in clumpy, irregular patterns. Their star formation occurs in sporadic bursts rather than steady, ongoing processes. These properties suggest that dwarf irregulars are governed by different physics than massive galaxies. The key difference is gravitational potential. Massive galaxies have deep potential wells that can organize gas into stable rotating disks. The gravitational field is strong enough to overcome turbulence and maintain coherent structures over billions of years. Dwarf galaxies have shallow potential wells where gravity is weaker. Turbulence driven by stellar feedback, supernova explosions and stellar winds can disrupt the gas distribution before it settles into organized structures. Each supernova explosion injects energy equivalent to 10 to the 51 ergs into the surrounding medium, enough to blow bubbles of hot gas hundreds of light years across. In a massive galaxy, this energy is negligible compared to the binding energy of the entire system. In a dwarf galaxy, it can disrupt the entire gas reservoir and drive significant mass loss into intergalactic space. This feedback-driven turbulence creates the irregular appearance of dwarf systems. The gas never settles into stable configurations. Star formation occurs in random locations where gas happens to reach sufficient density to collapse. The newly formed stars inject energy back into the gas, stirring it up and preventing further collapse. The result is a self-regulating cycle where star formation occurs in bursts separated by quiescent periods. During bursts, the galaxy brightens dramatically and shows concentrated regions of young blue stars. During quiescent periods, the gas disperses and star formation ceases until gravitational instabilities can compress the gas again. This cycle repeats irregularly over cosmic time, creating the patchy, asymmetric appearance that defines irregular galaxies. Some irregular galaxies are experiencing starburst episodes, periods of extraordinarily intense star formation that consume gas at rates hundreds of times higher than normal. These starbursts are often triggered by galaxy interactions or mergers, but can also occur spontaneously in gas-rich systems that undergo gravitational collapse. During a starburst, the galaxy's luminosity increases dramatically. The intense ultraviolet radiation from young massive stars ionizes surrounding gas, creating luminous nebulae that outshine the entire rest of the galaxy. The starburst typically lasts only 10 to 100 million years before exhausting the available gas supply. Afterward, the galaxy fades and enters a quiescent phase that can last billions of years. The most extreme starburst irregulars are called blue compact dwarfs, systems where star formation is so concentrated and intense that the entire galaxy appears as a single, bright blue knot. These galaxies have among the highest star formation rates per unit mass of any systems in the universe. They are converting their gas into stars so rapidly that they will exhaust their supplies within tens of millions of years. Why these galaxies are experiencing such extreme starbursts is unclear. Some appear to be late bloomers, systems that somehow avoided forming stars for most of cosmic history and are only now undergoing their first major star formation episode. Others might be experiencing merger-induced starbursts triggered by interactions with companion galaxies. The diversity of properties among blue compact dwarfs suggests that multiple pathways can lead to extreme starburst activity. Irregular galaxies also serve as laboratories for studying primordial star formation conditions. Because dwarf irregulars have low metallicity, with chemical compositions similar to what existed in the early universe, before stellar nucleosynthesis enriched the cosmos with heavy elements, they provide insights into how stars form in metal-poor environments. Observations show that metal-poor star formation produces different stellar populations than metal-rich star formation. The initial mass function, the distribution of stellar masses created during a star formation episode, appears to be weighted toward more massive stars in low metallicity environments. This means that early galaxies in the universe's youth would have formed proportionally more massive stars than modern galaxies do, affecting their chemical evolution and the radiation fields they produced. The Small Magellanic Cloud has a metallicity about 1/5 that of the Sun, making it one of the most metal-poor systems in the local group, where detailed stellar populations can be studied. Observations of star clusters in the SMC reveal that massive stars dominate the stellar populations more than they do in Milky Way clusters of similar age. This confirms theoretical predictions that metal-poor star formation favors massive stars. The implications extend to the early universe, suggesting that the first galaxies were dominated by massive stars that lived short lives, exploded as supernovae, and enriched their surroundings with heavy elements much more rapidly than modern stellar populations do. Some irregular galaxies show evidence of dark matter dominance even more extreme than in spiral galaxies. Rotation curve measurements of dwarf irregulars reveal that their mass-to-light ratios are among the highest in the universe. A typical dwarf irregular might contain 10 to 100 times more mass in dark matter than in visible stars and gas. This dark matter dominance means that the visible components are essentially tracer particles moving through dark matter halos. The irregular appearance reflects the distribution of visible matter, trying to respond to a dark matter potential well that is only partially filled. The visible galaxy is floating inside a much larger dark matter structure, like a small piece of debris trapped in a whirlpool. This dark matter dominance makes dwarf irregular galaxies ideal laboratories for testing dark matter models. Different dark matter theories predict different halo profiles and different responses to baryonic feedback processes. Observations of dwarf irregular rotation curves can distinguish between cold dark matter models, where dark matter particles are slow-moving and create sharply peaked density profiles, and warm dark matter models, where dark matter particles have higher velocities that smooth out small-scale structure. Current observations favor cold dark matter, but tensions remain. Some dwarf irregulars have rotation curves that are better fit by chord profiles, where density remains flat near the center, rather than the cuspy profiles predicted by pure cold dark matter simulations. This core cusp problem remains one of the outstanding challenges for dark matter theory. The classification of irregular galaxies into types IRRI and IRR2, distinguished by whether they resolve into individual stars in H2 regions or appear as diffuse unresolved light, is another projection effect masquerading as physical distinction. IRRI galaxies are simply closer to us, allowing our telescopes to resolve their stellar populations. IRR2 galaxies are more distant, appearing as diffuse patches because their individual stars are too faint to detect. The classification tells you about observational limitations, not about intrinsic galaxy properties. Both types are the same physical objects viewed at different distances. Modern taxonomy attempts to move beyond Hubble's irregular category by recognizing subtypes. Magellanic irregulars, abbreviated IM, show hints of spiral structure. Dwarf irregulars, abbreviated DI, lack any organized structure. Compact irregulars are small and dense. But these subcategories still rely on morphological description rather than physical understanding. They tell you what the galaxy looks like, not what processes created its appearance or how it will evolve. A true physical classification would organize irregulars by their star formation histories, their dark matter halo properties, their environmental contexts, and their evolutionary states. Shape would be a derived consequence, not a defining characteristic. The irregular classification also conflates multiple distinct formation pathways. Some irregulars are tidally disturbed spirals or ellipticals, systems whose original structures have been disrupted by interactions. Others are primordial irregulars, systems that never developed organized structure because their low masses prevented stable disk formation. Still others are post-starburst systems, galaxies that exhausted their gas supplies during intense star formation episodes and now appear irregular because they lack the gas needed to maintain structural coherence. These different origins produce superficially similar appearances, but reflect completely different evolutionary histories. Grouping them together under the irregular label obscures more than it reveals. The term irregular also carries the subtle implication that these galaxies failed to achieve proper structure, that they are defective versions of spirals or ellipticals. This anthropomorphic judgment has no physical basis. Irregular galaxies are not failures. They are systems operating under different conditions than massive disk galaxies, following different evolutionary pathways determined by their masses, their environments, and their merger histories. Their lack of symmetry is not pathology, but adaptation. They are shaped by forces that massive galaxies can resist, but dwarf systems cannot. Understanding irregular galaxies requires abandoning the expectation that all galaxies should look like the Milky Way, and accepting that cosmic structure formation produces a diversity of outcomes, depending on local conditions. When you look at an irregular galaxy, you are seeing a system where external forces have overwhelmed internal structure, where gravity is too weak to maintain order against turbulence and feedback, or where tidal interactions have scrambled whatever organization once existed. The irregular appearance is not randomness. It is the visible signature of physical processes operating at the margins of gravitational stability, where the balance between collapse and disruption creates morphologies that appear chaotic only because we do not yet fully understand the rules they are following. These galaxies are not disobedient. They are speaking a language we have not yet learned to decode. Between the spiral galaxies and the elliptical galaxies sits a category that should not exist. Lenticular galaxies, designated S0 in Hubble's classification system, possess the disk structures of spirals but lack spiral arms. They show the smooth light distributions of ellipticals but maintain distinct rotational support. They occupy the exact center of the tuning fork diagram, the convergence point where both prongs meet. This placement suggests they are transitional objects, systems caught between two states. But transition implies movement from one form to another. Lenticular galaxies are not moving. They are frozen. They are the cosmic equivalent of bodies preserved at the moment of death, systems that stopped evolving before reaching their final state. The existence of lenticular galaxies was recognized in the 1930s when astronomers noticed disk galaxies that showed no spiral structure but were clearly not ellipticals. These systems have prominent bulges, flattened disks, and often show dust lanes indicating the presence of gas and dust. But the disks are smooth and featureless, lacking the bright spiral arms and active star formation regions that define normal spirals. The S0 designation placed them at the junction between ellipticals and spirals, implying they might be evolutionary intermediates. But intermediates between what? And moving in which direction? Early theories proposed that S0 galaxies were spirals that had exhausted their gas supplies and could no longer form stars. Without ongoing star formation to trace out spiral density waves, the arms faded and the disk became smooth. This explanation seemed reasonable until astronomers measured the gas content of S0 systems and found that many contained significant amounts of neutral hydrogen, enough to support star formation if conditions were right. The gas exists but is not collapsing to form stars. Something is preventing the star formation process from occurring despite the presence of fuel. The answer involves ram pressure stripping and strangulation, two processes that can shut down star formation in disk galaxies without completely removing their gas. Ram pressure stripping occurs when a galaxy moves through the hot intracluster medium that fills galaxy clusters. The galaxy's motion creates a headwind of hot gas that exerts pressure on the cool gas disk. If the ram pressure exceeds the gravitational binding force holding the gas to the galaxy, the gas gets blown away and dispersed into the cluster environment. The galaxy loses its star-forming fuel and becomes unable to create new stars. The existing stellar disk remains intact, creating a lenticular morphology. Strangulation is more subtle. When a galaxy falls into a cluster, the hot halo of gas surrounding the galaxy can be stripped away by tidal interactions and ram pressure before the cool disk gas is affected. This hot halo normally provides a reservoir of gas that can cool and fall onto the disk, replenishing the star-forming material as it gets consumed. Without the halo, the galaxy is cut off from its gas supply. It can continue forming stars for a while using its existing disk gas, but once that gas is exhausted, star formation ceases. The galaxy strangles slowly over hundreds of millions of years, gradually transforming from a spiral into an S0 as its star formation fades. Both processes predict that S0 galaxies should be common in galaxy clusters, where ram pressure and tidal interactions are strong, and rare in the field where galaxies are isolated. Observations confirm this prediction. Approximately 50% of massive disk galaxies in dense clusters are lenticulars, compared to less than 20% in low-density environments. The fraction increases further in the cluster cores where environmental effects are strongest. S0 galaxies are therefore environmentally created objects, spirals that have been transformed by their surroundings. But this environmental explanation cannot be the complete story. Some S0 galaxies exist in relatively isolated environments where ram pressure stripping should be negligible. These field lenticulars must have formed through different processes. One possibility is that they are ancient galaxies that formed their stars very early in cosmic history and exhausted their gas supplies billions of years ago through internal processes rather than environmental stripping. Another possibility is that they experienced gas-poor mergers, collisions with other galaxies that added stellar mass without bringing significant amounts of gas. Such mergers would preserve the disk structure while removing or heating the gas, creating lenticular morphology. The bulge-to-disk ratios of S0 galaxies provide additional clues about their formation. S0 systems tend to have larger bulges relative to their disks compared to spiral galaxies. This suggests that whatever process created them also built up the central stellar concentration. Galaxy mergers naturally create this effect because the merger process funnels gas and stars toward the center, feeding the bulge and potentially triggering central star formation. Environmental processes like ram pressure stripping do not obviously explain bulge growth, suggesting that at least some S0 galaxies formed through merger-related processes. The rotation properties of S0 galaxies fall between spirals and ellipticals. They show organized rotation like spirals, with stars moving coherently around the galactic center. But they also show significant velocity dispersion, random motions that create pressure support in addition to rotational support. This combination suggests that S0 disks are dynamically hotter than spiral disks, meaning their stars have more random motion relative to their ordered rotation. The heating could come from minor mergers, gravitational interactions with passing satellites that inject kinetic energy into the disk, and increase velocity dispersion without completely destroying the disk structure. Some S0 galaxies show evidence of recent or ongoing gas accretion despite their lack of internal star formation. Cold gas streams falling onto the galaxy from the intergalactic medium can replenish the gas supply. But if the gas cannot cool efficiently, or if feedback processes heat it before it can collapse, star formation remains suppressed. These systems exist in a frustrated state where fuel is present but ignition is prevented by environmental or internal conditions. They represent a different kind of transition, not from spiral to lenticular, but from lenticular, potentially back towards spiral if conditions change. The edge-on appearance of S0 galaxies reveals another mystery. Many show prominent dust lanes bisecting their disks, indicating the presence of cold gas and dust despite the lack of star formation. The dust lanes are often highly structured, showing warps, kinks, or asymmetries that suggest recent accretion or tidal disturbances. But the dust content is typically much lower than in spiral galaxies, consistent with gas depletion through environmental processes. The small amount of remaining dust traces the residual gas that was not completely removed during the transformation from spiral to lenticular. The central regions of S0 galaxies sometimes contain nuclear star clusters, dense concentrations of stars at the galactic nucleus, with masses ranging from 100,000 to 10 million solar masses. These clusters are distinct from the supermassive black holes that occupy the centers of most massive galaxies. Their origin is debated. They might form through in situ star formation in the nucleus, with gas funneled to the center by gravitational torques. Or they might form through the infall and merger of star clusters that spiral toward the center through dynamical friction. The presence of nuclear star clusters in S0 galaxies, but not in all spirals or ellipticals, suggests they might be connected to the transformation process that creates lenticular morphology. Some S0 galaxies are classified as S0A or S0/A, indicating they show extremely faint spiral structure, visible only in deep imaging or in specific wavelength bands. These systems blur the boundary between lenticulars and spirals, representing objects where spiral density waves are present, but so weak that they barely trace out visible arms. The weakness of the spiral structure might indicate that the density waves are dissipating due to lack of gas to maintain them, or that the galaxy is in the process of transforming from spiral to lenticular, as environmental effects gradually remove its gas. The color distributions of S0 galaxies provide timing information about when they stopped forming stars. Most S0s are red, indicating old stellar populations, dominated by low-mass stars that have been shining for billions of years. But some show blue cores or rings, indicating recent star formation in specific regions. These blue features suggest that star formation shutdown was not uniform across the galaxy, but occurred in stages, with the outer disk quenching first and the central regions continuing to form stars for longer. The detailed history of star formation shutdown is encoded in the spatial distribution of stellar populations, which can be recovered through detailed spectroscopy and population modeling. The existence of S0 galaxies creates a philosophical problem for galaxy classification. If lenticulars are simply gas-poor spirals, do they deserve their own category? Should we classify galaxies by their morphology or by their physical properties, like gas content and star formation rate? The morphological approach groups together objects that look similar but formed through different processes. The physical approach would separate objects that look similar but are in different evolutionary states. Neither system is objectively correct. Classification is a human construct designed to organize observations, and different classification schemes serve different purposes. Modern surveys using integral field spectroscopy can measure stellar kinematics across entire galaxy faces, revealing how S0 galaxies support themselves against gravitational collapse. The observations show that S0s are kinematically diverse. Some are fast rotators, with most of their support coming from ordered rotation, making them dynamically similar to spirals. Others are slow rotators with significant pressure support from random stellar motions, making them dynamically similar to ellipticals. This kinematic diversity indicates that the S0 classification encompasses multiple distinct types of objects that happen to share similar visual appearances but have different internal structures. The future evolution of S0 galaxies depends on their environment. Systems and clusters will likely remain lenticular indefinitely unless they merge with other galaxies, in which case they will become ellipticals. Systems in lower density environments might accrete new gas from the intergalactic medium or from minor mergers, potentially restarting star formation and transforming back toward spiral morphology. Galaxy evolution is not a one-way street from spiral to lenticular to elliptical. Under the right conditions, galaxies can move backward through this sequence, regaining star formation and spiral structure after periods of quiescence. The connection between S0 galaxies and the broader problem of galaxy quenching, the shutting down of star formation across entire populations, makes them crucial for understanding cosmic evolution. The universe's overall star formation rate has been declining for the past 10 billion years. Fewer stars are forming now than at the peak of cosmic star formation activity, when the universe was only 3 billion years old. This decline is driven partly by the exhaustion of gas supplies, as star formation converts hydrogen into stars, but also partly by the growth of galaxy clusters and the environmental processes that transform spirals into lenticulars and ellipticals. Understanding how and why galaxies become S0s is therefore essential for understanding why the universe is gradually running out of star formation activity. When you observe a lenticular galaxy, you are witnessing death by starvation. Not the violent death of a collision that creates an elliptical, but the slow death of isolation from fuel supplies. The galaxy's existing stars will continue burning for billions of years, but no new generations will replace them when they die. The system is winding down, exhausting its stellar populations one star at a time, fading gradually from view as massive, luminous stars exhaust themselves, and only dim red dwarfs remain. In 100 billion years, the S0 galaxy will be a graveyard of white dwarfs and neutron stars, invisible except through gravitational effects, a fossil structure marking the location where stars once shone. The smooth, featureless disk you see today is already a corpse. It simply has not finished cooling yet. In 1974, astronomer Art Hogue was examining photographic plates from the Las Campanas Observatory in Chile when he encountered something impossible. A perfectly circular ring of blue stars floating in space with a yellow nucleus at the center and empty darkness between them. The ring and the nucleus were separated by a gap containing no visible matter, creating an object that looked less like a galaxy and more like a cosmic target painted across the void. Hogue did not know what he was looking at. He labeled it as a planetary nebula in his notes, then later as a peculiar galaxy. The object was eventually named Hogue's object in his honor, and it remains one of the most mysterious structures ever observed. Ring galaxies are exactly what they sound like: circular or elliptical structures of stars and gas arranged in ring configurations rather than disks, spirals, or ellipsoids. The rings are not thin like Saturn's rings. They are thick structures containing billions of stars, spread across diameters of 100,000 light-years or more. And they defy every model of galaxy formation that astronomers have developed. Stable rotating disks make sense. Pressure-supported ellipsoids make sense. But rings? Rings should not be gravitationally stable. They should either collapse inward toward the center or disperse outward into space. Yet ring galaxies exist, persisting for hundreds of millions of years with no obvious mechanism to maintain their structure. The standard explanation for ring galaxies invokes collision processes. When a small, dense galaxy passes directly through the center of a larger disk galaxy, it creates a gravitational disturbance that propagates outward as a density wave. This wave compresses gas as it expands, triggering a ring of star formation that moves radially through the disk like a ripple on a pond. The collision is almost perfectly head-on, with the intruder galaxy punching through the disk and emerging on the other side. The intruder's gravitational field pulls material inward as it approaches, then releases it as it passes through, creating an expanding ring of compressed gas. Computer simulations of these collisional ring formations successfully reproduce many observed features. The rings expand at velocities of 100 to 200 kilometers per second. They show enhanced star formation, creating bright blue populations of young massive stars. They sometimes show multiple concentric rings if the collision involved multiple components, or if the rings have time to form, expand, and trigger secondary rings through the same compression mechanism. The Cartwheel Galaxy is the most spectacular example of this formation process, showing a bright outer ring approximately 150,000 light-years in diameter surrounding a disturbed inner disk with spoke-like features connecting them. But Hogue's object does not fit the collision model. The object shows no obvious companion galaxy that could have caused the collision. The central nucleus appears undisturbed, with no signs of recent tidal interactions. The ring itself is too symmetrical and too isolated from the nucleus to be an expanding density wave. If Hogg's object formed through a collision, the collision must have occurred billions of years ago, and the intruder galaxy has long since moved away beyond detection range. But the ring's sharp edges and active star formation suggest it is not ancient but relatively young, only a few 100 million years old at most. Alternative formation mechanisms have been proposed. One model suggests that Hogg's object is a polar ring galaxy viewed face-on. Polar ring galaxies are systems where a ring of gas and stars orbits perpendicular to the main galactic disk, creating structures that look completely different depending on viewing angle. If you view a polar ring edge-on, you see a central disk with rings extending above and below like wings. If you view it face-on, you see what looks like a detached ring surrounding a nucleus. This interpretation requires the ring and the nucleus to be kinematically distinct components that somehow became gravitationally bound. Another model proposes that Hogg's object formed through the accretion of gas from the intergalactic medium. If gas falling onto the galaxy has significant angular momentum, it cannot fall directly onto the nucleus but must settle into an extended ring structure where centrifugal forces balance gravitational attraction. Over time, this ring can fragment and form stars, creating a luminous ring separated from the central stellar population. This model requires specific conditions to work. The infalling gas must have very high angular momentum and must arrive in a configuration that creates a ring rather than a disk. These conditions are not impossible, but seem contrived for explaining a single object. The most disturbing possibility is that Hogg's object represents a previously unknown class of galaxy that forms through processes we have not identified. If this is true, other similar objects should exist. And they do. Several Hogg-type galaxies have been discovered, though they remain extremely rare. The Southern Ring Galaxy shows similar morphology, with a prominent blue ring surrounding a red nucleus. These systems suggest that whatever process creates Hogg's object is not unique, but operates under conditions that are uncommon enough to make such galaxies rare. Resonant ring galaxies represent another category of ring structure with completely different origins. These rings form at specific radii in disk galaxies, where orbital periods match the rotation rate of a bar or spiral pattern. At these resonance locations, gas accumulates and triggers star formation, creating rings that are actually parts of the disk rather than separate structures. The rings are often incomplete, showing enhanced star formation on one side where gas is being compressed, and depleted regions on the other side where gas has been consumed. These resonant rings are common in barred galaxies, and do not pose the same theoretical problems as detached rings like Hogg's object. Nuclear rings are even more common, appearing in the central kiloparsec of many barred galaxies. These rings form where gas funneled inward by the bar reaches an inner resonance and piles up, unable to fall further toward the nucleus. The accumulated gas collapses and forms stars, creating bright rings surrounding the galactic center. Nuclear rings are sites of intense star formation and can contain significant fractions of a galaxy's total star formation activity, despite occupying very small regions. The Milky Way itself may possess a molecular ring at a radius of approximately 400 parsecs from the galactic center, though the ring is not complete and shows significant asymmetries. Polar ring galaxies deserve special attention because they represent the most extreme departure from normal galactic structure. These systems consist of a central elliptical or lenticular galaxy surrounded by a ring of gas and stars that orbits perpendicular to the main body. The ring can be nearly as massive as the central galaxy and extends to radii exceeding the visible extent of the central component. The two components are kinematically distinct, rotating in different planes with no obvious connection between their stellar populations. The origin of polar rings is debated. One model proposes that they form through the accretion of material from a companion galaxy during a merger. If the companion approaches on a perpendicular orbit, its debris can settle into a polar ring configuration rather than merging with the main body. Another model suggests that polar rings form when a galaxy accretes cold gas streams from the intergalactic medium. These streams can arrive from any direction, and if they have angular momentum perpendicular to the galaxy's rotation, they will settle into polar configurations. The existence of polar rings provides a unique opportunity to measure the three-dimensional shape of dark matter halos. Normal disk galaxies only reveal the projected mass distribution, making it difficult to determine whether dark matter halos are spherical, oblate, or prolate. Polar ring galaxies give us two orthogonal views of the gravitational potential, allowing direct measurement of halo shape. Observations show that dark matter halos are approximately spherical or slightly oblate, consistent with predictions from cold dark matter simulations. This is one of the few direct measurements of dark matter halo geometry available to astronomers. The rarity of ring galaxies tells us something important about galaxy formation. If rings could form through common processes, they should be abundant. Their scarcity indicates that the conditions required for ring formation are unusual. Collisional rings require nearly perfect head-on impacts between galaxies, events that are rare because most collisions are oblique. Polar rings require specific accretion geometries that are uncommon in the cosmic web's filamentary structure. Resonant rings require bars or spiral patterns with specific rotation speeds and gas supplies at the right radii. Each type of ring forms under narrow conditions, making rings collectively uncommon despite multiple formation pathways. Some ring galaxies show evidence of multiple rings at different radii, creating nested structures that look like cosmic archery targets. The Cartwheel Galaxy shows at least two distinct rings. An inner ring at approximately 50,000 light-years from the center, and an outer ring at 150,000 light-years. The multiple rings might represent different epochs of the same collision, with the inner ring forming first as the initial density wave passed through, and the outer ring forming as a secondary wave followed. Or they might represent completely separate events, multiple collisions at different times creating independent ring structures. The colors of ring galaxies provide clues about their ages and star formation histories. Young rings are blue, dominated by massive O and B-type stars with ages less than 100 million years. These young stars trace recent star formation triggered by the collision or accretion event that created the ring. Older rings are redder, indicating that star formation has ceased and the stellar population is aging. The reddest rings might be several billion years old, ancient structures that have exhausted their gas supplies and now contain only long-lived, low-mass stars. The transition from blue to red marks the life cycle of a ring galaxy, from violent formation through active star formation to eventual quiescence. The stability of ring structures over cosmic time remains poorly understood. Rings should be vulnerable to perturbations from interactions with passing galaxies or from internal instabilities that cause the ring to fragment or collapse. Yet some rings persist for billions of years, maintaining their circular configurations despite these threats. The rings must be supported by some combination of rotation, pressure gradients, and possibly magnetic fields that prevent gravitational collapse. But the exact balance of forces varies from system to system, and no unified model explains the stability of all observed rings. The discovery of ring galaxies at high redshift, in the distant universe when galaxies were younger and interactions were more common, suggests that ring formation might have been more frequent in the past. The early universe had higher galaxy densities, increasing collision rates. It also had more gas available, making rings more luminous and easier to detect when they formed. As the universe evolved and expanded, collision rates decreased and gas supplies were depleted through star formation. Ring galaxies became progressively rarer, evolving into the unusual objects we see today. When you observe a ring galaxy, you are witnessing the aftermath of a cosmic catastrophe captured in a temporary frozen configuration. The ring is not permanent. It is a transient structure that will eventually disperse or collapse over hundreds of millions of years. The stars in the ring will scatter as gravitational interactions with the main galaxy alter their orbits. The gas will be consumed by star formation or blown away by stellar winds and supernova explosions. What remains will be a disturbed disk galaxy, showing faint traces of its ring past visible only in velocity fields or stellar population distributions. The perfect geometric ring you see in photographs is already dissolving. You are seeing it during the brief window when the structure is coherent enough to be recognizable. A moment frozen in cosmic time that will not persist into the distant future. Ring galaxies are therefore not a stable galaxy type but a phase that certain systems pass through during their evolution. They represent moments of structural reorganization following violent events, temporary configurations that exist for a fraction of cosmic history before resolving into more stable morphologies. The classification of rings as a distinct galaxy type is misleading. They are not types but states, snapshots of transformation captured during brief intervals when gravitational forces have arranged matter into geometries that defy our expectations and challenge our understanding of what galaxies can be. The term dwarf suggests something small and harmless. Astronomers use it to describe galaxies containing fewer than 10 billion stars, systems that are tiny compared to the Milky Way's 400 billion stellar population. The name implies insignificance, objects too small to matter in the grand cosmic scheme. This implication is catastrophically wrong. Dwarf galaxies are not harmless, they are predators. And they are currently consuming your home galaxy one piece at a time. The Sagittarius dwarf elliptical galaxy is right now being torn apart by the Milky Way's gravitational field. This small system, containing only several tens of millions of stars, is stretched across more than 1 million light-years of space as tidal forces rip it into streams. But before you celebrate our galaxy's dominance, understand this. The Sagittarius dwarf is not a victim. It is ammunition. Every star it loses becomes part of the Milky Way's halo, altering our galaxy's structure and adding mass that increases our gravitational influence. And Sagittarius is just one of dozens of dwarf galaxies currently orbiting the Milky Way, each one either being consumed or preparing to collide. Dwarf galaxies are the most common type of galaxy in the universe by number. For every massive spiral or elliptical galaxy, there are hundreds of dwarf systems lurking in the cosmic void. Most are invisible in optical surveys because they contain so few stars that their surface brightness falls below detection thresholds. They exist as dark matter halos containing sparse populations of stars, ghost structures that betray their presence only through gravitational effects or through emission lines from their gas content. The universe is not dominated by the massive bright galaxies you see in photographs. It is dominated by these small dark systems that collectively contain more mass than all the giant galaxies combined. The local group, the gravitationally bound collection of galaxies containing the Milky Way and Andromeda, hosts over 80 known members. Approximately 75 of them are dwarf galaxies. The Milky Way alone has at least 60 satellite dwarfs orbiting within 400 kiloparsecs of the galactic center. Some are well-studied systems, like the Large and Small Magellanic Clouds. Others are ultra-faint dwarfs, discovered only in the last 2 decades by deep surveys like the Sloan Digital Sky Survey. These ultra-faint systems contain as few as 1,000 stars spread across regions hundreds of light-years across, making them so diffuse that they barely qualify as bound objects. But do not mistake faintness for impotence. Dwarf galaxies are the building blocks from which all massive galaxies formed. In the hierarchical structure formation paradigm, small dark matter halos collapse first in the early universe. These halos accrete gas and form stars, creating the first dwarf galaxies. Over time, dwarves merge with each other, building progressively larger systems through a process of continuous cannibalism. The Milky Way is not a primordial object, but an accumulation of hundreds or thousands of dwarf galaxies that merged over the past 13 billion years. You are living inside a graveyard, constructed from the corpses of consumed dwarfs. The evidence for this cannibalistic history is preserved in the Milky Way's stellar halo. When a dwarf galaxy gets tidally disrupted, its stars are scattered along its orbital path, creating stellar streams that can be traced across the sky. The Sagittarius stream wraps around the Milky Way multiple times, marking the orbital path where the Sagittarius dwarf has been losing stars for the past few billion years. The Orphan Stream, the Monoceros Ring, and dozens of other stellar streams have been identified in the halo, each one the fossil remnant of a destroyed dwarf galaxy. The halo is not a smooth distribution, but a complex web of streams, shells, and overdensities that record every accretion event in the Milky Way's history. Chemical abundance patterns in halo stars provide additional forensic evidence of dwarf galaxy accretion. Stars from different dwarf galaxies have different chemical compositions, reflecting their unique star formation histories. When these dwarfs merge with the Milky Way, their stars retain their chemical signatures. By measuring element abundances in thousands of halo stars, astronomers can identify chemically distinct populations and trace them back to their parent dwarf galaxies. This chemical tagging reveals that the halo is not homogeneous, but contains dozens of distinct populations, each originating from a separate dwarf system. Some dwarf galaxies survive the accretion process and continue orbiting as satellites rather than being immediately destroyed. But survival is temporary. Each orbital passage through the Milky Way's disk and halo strips away more stars and gas through tidal forces and ram pressure. The dwarf gradually shrinks, losing mass until eventually only its core remains. The final remnant is a globular cluster, a compact collection of a few 100,000 stars that was once the nucleus of a much larger galaxy. Many of the Milky Way's 150 globular clusters may be the cores of ancient dwarf galaxies that were completely consumed except for their dense central regions. Dwarf galaxies are also the most dark matter-dominated objects in the universe. Measurements of dwarf galaxy rotation curves reveal mass-to-light ratios exceeding 1,000 in some cases, meaning they contain 1,000 times more mass in dark matter than in visible stars. The stars are essentially tracer particles floating in vast dark matter halos. For comparison, the Milky Way's mass-to-light ratio is approximately 10 to 30 depending on how you measure it. Dwarfs are almost pure dark matter with tiny stellar populations marking the halo centers. This extreme dark matter dominance makes dwarf galaxies crucial laboratories for testing dark matter theories. The distribution of dark matter in dwarf halos is sensitive to the properties of dark matter particles. Cold dark matter predicts that halos should have cuspy density profiles where density increases sharply toward the center. Warm dark matter predicts chord profiles where central density is relatively flat. Observations of dwarf galaxy rotation curves show evidence for both types of profiles, creating the core cusp problem that remains unresolved. Either cold dark matter simulations are missing important physics like stellar feedback that can transform cuspy profiles into chord ones, or dark matter has properties beyond what standard cold dark matter models assume. Dwarf spheroidal galaxies represent the most extreme example of dark matter dominance. These systems are almost devoid of gas and show no signs of recent star formation. They consist of ancient stellar populations embedded in massive dark matter halos. Their stellar velocity dispersions, measures of how fast stars are moving randomly, are much higher than their luminosities suggest, indicating enormous hidden mass. Some dwarf spheroidals have mass-to-light ratios exceeding 3,000, making them the darkest galaxies known. They are essentially invisible, except for their gravitational effects and the faint light from their sparse stellar populations. The formation of dwarf spheroidals is linked to environmental processes. Many appear to be dwarf, irregular galaxies that lost their gas through ram pressure stripping as they orbited through the Milky Way's halo. Without gas, they cannot form new stars and gradually fade as existing stars age. The transformation from gas-rich, irregular to gas-poor spheroidal mirrors the transformation from spiral to lenticular in massive galaxies, showing that similar environmental processes operate across the full range of galaxy masses. But not all dwarfs are passive victims of environmental stripping. Some dwarf galaxies undergo intense starburst episodes, where they form stars at rates comparable to much more massive systems. These starburst dwarfs can temporarily outshine normal disk galaxies, despite having 1/100th the stellar mass. The starbursts are often triggered by interactions with other dwarfs, or by gravitational interactions with the massive galaxies they orbit. During the burst, the dwarf's luminosity increases by factors of 10 or more. Supernovae from the newly formed massive stars inject enormous amounts of energy into the surrounding gas, driving winds that can expel significant fractions of the dwarf's baryonic mass into intergalactic space. These winds are supernova-driven outflows, moving at velocities exceeding 500 kilometers per second. In a massive galaxy, such winds are confined by the deep gravitational potential well and cannot escape. But in dwarfs, the shallow potential wells allow winds to escape entirely, removing gas that could otherwise form future generations of stars. This self-regulation mechanism explains why dwarf galaxies are inefficient at forming stars. They convert only a small percentage of their available gas into stars before feedback processes blow the rest away. The missing satellites problem represents one of the major challenges for our understanding of dwarf galaxy formation. Cold, dark matter simulations predict that massive galaxies like the Milky Way should be surrounded by thousands of dark matter subhalos, small clumps orbiting within the main halo. But observations find only about 60 to 80 satellite galaxies around the Milky Way, a factor of 10 to 100 less than predicted. Either most dark matter subhalos fail to form stars and remain completely dark, or the simulations are over-predicting the number of subhalos due to missing physics. Recent discoveries of ultra-faint dwarf galaxies partially alleviate this problem. These systems are so faint that they were invisible in older surveys, and new observations keep finding more. The current count of Milky Way satellites is approximately 80, up from about 15 known in the year 2000. As deeper surveys probe fainter surface brightness limits, more ultra-faint dwarfs will likely be discovered. But even accounting for all possible faint systems, the observed number still falls short of predictions by significant factors. Something is suppressing dwarf galaxy formation or destroying them after they form. Tidal destruction is one possibility. Dwarf galaxies orbiting through the Milky Way's disk can be completely disrupted by tidal forces within a few orbital passages. The disrupted stars join the stellar halo, and the dark matter halo disperses or remains as a dark substructure without visible stars. This process reduces the number of observable satellites while preserving the total number of dark matter subhalos. Simulations show that tidal destruction can account for a significant fraction of the missing satellites, but not all. Reionization heating is another possibility. When the first stars formed in the universe and began emitting ultraviolet radiation, they ionized the surrounding hydrogen gas, heating it to tens of thousands of degrees. This heating increased the gas pressure and prevented gas from collapsing into small dark matter halos. Only halos above a certain mass threshold could overcome the increased pressure and form stars. This filtering effect would suppress dwarf galaxy formation in small halos, reducing the number of visible satellites while leaving the dark matter subhalos intact. The threshold mass is uncertain but might be around 1 million to 10 million solar masses, consistent with the masses of the faintest observed dwarfs. Dwarf galaxies at high redshift in the distant early universe look completely different from local dwarfs. James Webb Space Telescope observations reveal that early dwarfs are clumpy, irregular, and actively forming stars at high rates. They show none of the quiescent properties of local dwarf spheroidals. This evolutionary difference reflects the changing environmental conditions and gas supplies available to dwarfs at different cosmic epochs. Early dwarfs are gas-rich and actively growing. Local dwarfs are gas-poor and fading, having been stripped by their massive neighbors or having exhausted their supplies through star formation. The discovery of isolated dwarf galaxies and cosmic voids challenges the idea that all dwarfs must be satellites of massive galaxies. These void dwarfs are separated from any massive galaxy by millions of light years and have evolved in near-complete isolation. They show different properties than satellite dwarfs, retaining more gas and forming stars at steadier rates because they are not subject to environmental stripping. Comparing void dwarfs to satellite dwarfs reveals how environmental effects shape dwarf galaxy evolution, providing natural experiments where the only difference is the presence or absence of a massive neighbor. The role of dwarf galaxies in cosmic chemical evolution is profound. Because dwarfs experience strong outflows that expel metal-enriched gas into the intergalactic medium, they are efficient polluters of their surroundings. The metals created in dwarf galaxy stars do not remain in the dwarfs, but are dispersed across vast volumes, enriching the gas from which future galaxies will form. This pollution process means that even dwarf galaxies that are eventually destroyed have lasting impacts on cosmic evolution, seeding the intergalactic medium with the heavy elements necessary for planet formation and life. When you look at a dwarf galaxy, you are looking at both the past and the future. The past, because these systems preserve conditions from the early universe better than massive galaxies that have been thoroughly processed by billions of years of star formation and merging. The future, because dwarf galaxies orbiting the Milky Way will eventually be consumed, their stars added to our halo, their dark matter halos merged with ours, contributing to the ongoing growth of our galaxy through cannibalism. The small size of dwarfs is deceptive. They are not insignificant. They are the fundamental building blocks of cosmic structure, the seeds from which all galaxies grew, and the predators that are even now tearing apart and reconstituting the massive systems we call home. In 2015, astronomers examining images of the Coma Cluster discovered 47 galaxies that should not exist. These systems were the size of the Milky Way, spanning 100,000 light-years from edge to edge, but contained only 1% of the stars. They were so diffuse, so spread out across space, that they barely registered as distinct objects. Their surface brightness was so low that they would have been completely invisible in previous surveys. Scientists called them ultra-diffuse galaxies, or UDGs, but that clinical name conceals a terrifying reality. These are ghost galaxies, failed systems that somehow grew to enormous sizes while accumulating almost no stars. They are dark matter structures with just enough visible matter to mark their locations. And they are everywhere. Ultra-diffuse galaxies violate the fundamental relationship between galaxy size and stellar mass that holds for all other galaxy types. Normal galaxies follow a tight scaling relation where more massive galaxies are larger. Double the stellar mass and you increase the size by a predictable factor. This relationship reflects how galaxies form through the collapse of dark matter halos, with more massive halos creating larger galaxies. Ultra-diffuse galaxies break this relationship completely. They have the sizes of massive galaxies but the stellar masses of dwarfs. They occupy a region of parameter space that should be empty according to all galaxy formation models. The Dragonfly Telephoto Array, a specialized telescope designed to detect extremely low surface brightness structures, revolutionized the study of ultra-diffuse galaxies by discovering hundreds of them in nearby galaxy clusters. The Dragonfly uses multiple camera lenses working together to suppress scattered light and reveal faint extended structures invisible to conventional telescopes. Its discovery showed that UDGs are not rare anomalies, but a significant population making up approximately 10 to 20% of all galaxies and clusters by number. They were hiding in plain sight, too faint to be detected by standard surveys but abundant enough to constitute a major component of cluster galaxy populations. The extreme diffuseness of these systems creates bizarre properties. Their stellar density is so low that if you were standing on a planet in an ultra-diffuse galaxy, you would see far fewer stars in your night sky than we see from Earth. The spacing between stars is several times larger than in the solar neighborhood. The galaxy would be barely visible from the inside, appearing as a faint haze of scattered stars. Rather than the rich star fields we associate with galactic disks, you would be living inside a galaxy that looks from the inside almost indistinguishable from intergalactic space. The formation of ultra-diffuse galaxies is one of the most active debates in extragalactic astronomy. One model proposes that they are dwarf galaxies that experienced unusually rapid spin during formation. High angular momentum causes the collapsing gas to settle into extended configurations rather than compact disks. The result is a galaxy with normal dwarf mass but abnormally large size. This model can explain the diffuse structure, but struggles to explain why some dwarfs acquire such high spin, while most do not. Another model invokes environmental effects. When a dwarf galaxy falls into a massive galaxy cluster, it experiences tidal forces and ram pressure that can puff up its structure. Tidal heating adds kinetic energy to the stars, causing them to move on more extended orbits. Ram pressure strips away gas, preventing the galaxy from collapsing further and allowing existing stars to remain in diffuse configurations. Over time, the galaxy expands to several times its original size, while losing most of its gas and star-forming ability. This model naturally explains why ultra-diffuse galaxies are common in clusters, where environmental effects are strong and rare in the field where galaxies evolve in isolation. A third model proposes that ultra-diffuse galaxies are the most extreme examples of failed galaxies. systems where star formation was suppressed so strongly that they formed very few stars. Despite residing in massive dark matter halos, feedback processes like supernova-driven winds or reionization heating prevented most of the available gas from collapsing, leaving behind galaxies that are mostly dark matter with just a trace stellar population. The discovery of globular clusters orbiting ultra-diffuse galaxies provided crucial clues about their nature. Some UDGs host dozens of globular clusters, far more than expected for systems with such low stellar masses. The Milky Way contains about 150 globular clusters and has roughly 400 billion stars. An ultra-diffuse galaxy with only 1 billion stars should have less than one globular cluster on average. Instead, some UDGs have 20, 30, or even 70 globular clusters. This enormous excess suggests that UDGs reside in more massive dark matter halos than their stellar masses indicate. They are not simply expanded dwarfs, but genuinely massive systems that failed to form stars efficiently. The globular cluster populations also reveal information about UDG formation histories. Globular clusters form during intense bursts of star formation in the early universe. A galaxy with many globular clusters must have experienced significant star formation activity at some point in its past, even if it is now quiescent and diffuse. This rules out scenarios where UDGs never formed many stars. Instead, they must have formed substantial stellar populations early on and then either had those stars stripped away by environmental effects or distributed them across enormous volumes through expansion processes. DF2 and DF4 are two ultra-diffuse galaxies in the NGC 1028 group that became famous for apparently containing no dark matter. Initial observations suggested these systems had stellar velocity dispersions consistent with their visible mass alone, implying negligible dark matter contributions. This discovery was shocking because every other galaxy observed shows clear evidence of dark matter dominance. Galaxies without dark matter should not exist according to standard formation models. The finding triggered intense follow-up observations and theoretical debates. Subsequent studies have challenged the no dark matter interpretation. Revised distance measurements place DF2 and DF4 closer to us than initially estimated, which changes the inferred sizes and masses. The new distances suggest these systems do contain significant dark matter after all, though possibly less than typical galaxies of similar size. The debate continues with different teams obtaining conflicting measurements using different methods. The uncertainty reflects the difficulty of studying such faint diffuse objects, where even basic properties like distance are challenging to measure accurately. If DF2 and DF4 truly contain little dark matter, they would require exotic formation scenarios. One possibility is that they formed as normal dark matter halos but lost their dark matter through tidal interactions during close passages with massive galaxies. Simulations show that tidal forces can preferentially strip dark matter from the outer regions of galaxies while leaving the stellar component relatively intact. Repeated tidal encounters could gradually remove most of a galaxy's dark matter halo. Another possibility is that these systems are tidal dwarfs, galaxies formed from gas and stars torn from larger galaxies during mergers. Tidal dwarfs would initially contain little dark matter, because the tidal material is stripped from the outer disks of the parent galaxies, where baryonic matter dominates locally over dark matter. Ultra-diffuse galaxies also exist in isolation in cosmic voids and in the field between clusters. These isolated UDGs cannot invoke cluster environmental effects for their formation. They must have formed through internal processes alone. Comparing isolated UDGs to cluster UDGs reveals which formation mechanisms are universal and which are environment-specific. Preliminary results suggest isolated UDGs tend to be slightly less diffuse and more likely to contain gas, consistent with the expectation that environmental stripping contributes to extreme diffuseness in clusters. The stellar populations of ultra-diffuse galaxies show that most are old systems with ages exceeding 10 billion years. Their stars formed early in cosmic history and have been evolving passively ever since. This ancient age implies that whatever processes created their diffuse structure operated during their formation rather than being imposed recently. They are not newly expanded galaxies, but have been diffuse since their youth. The old stellar ages also explain their faintness. Old stellar populations are dominated by low-mass red stars that produce little light. The lack of young blue stars means UDGs emit primarily in red and infrared wavelengths where they are even harder to detect. Some ultra-diffuse galaxies show evidence of recent or ongoing tidal disruption. They display elongated morphologies, tidal tails, or asymmetric distributions suggesting they are being torn apart by gravitational interactions with massive neighbors. These disrupting UDGs provide insights into what happens to diffuse systems when they encounter strong tidal fields. Because UDGs are so loosely bound, they are especially vulnerable to tidal disruption. A tidal force that would barely perturb a compact galaxy can completely shred an ultra-diffuse system, dispersing its stars across vast regions of space. The relationship between ultra-diffuse galaxies and dwarf ellipticals is unclear. Both types are faint systems with old stellar populations. The main difference is size. Dwarf ellipticals are compact while UDGs are extended. But this distinction might be artificial, representing opposite ends of a continuous distribution rather than two distinct types. Some systems fall in the intermediate range between dwarf ellipticals and UDGs, showing properties of both. A unified understanding would explain how galaxies populate the full range from very compact to extremely diffuse, and what physical processes determine where individual systems land in this distribution. The mass-to-light ratios of ultra-diffuse galaxies are among the highest measured for any galaxy type, often exceeding 1,000 within their half-light radii. This means they are almost pure dark matter by mass, with visible stars contributing less than 0.1% of the total mass. They are the ultimate dark matter-dominated objects, more extreme even than dwarf spheroidals. Studying UDGs, therefore, provides insights into dark matter properties. Under conditions where baryonic matter is nearly negligible, any deviations from cold dark matter predictions should be especially apparent in systems where dark matter so completely dominates. The discovery of ultra-diffuse galaxies forces us to expand our concept of what constitutes a galaxy. Traditional definitions require galaxies to be gravitationally bound collections of stars with sufficient density to be distinguishable from the background. UDGs barely meet this definition. Their stellar densities are so low that they blend into the intracluster light, the diffuse population of unbound stars filling galaxy clusters. Some UDGs might not even be bound objects but transient structures in the process of dissolving into intracluster light. Drawing the boundary between very diffuse bound galaxies and very clumpy intracluster light becomes arbitrary at extreme diffuseness. Future deep surveys will likely discover even more extreme examples of low surface brightness galaxies. The current detection limits are set by instrumental capabilities, not by any physical limits on how diffuse galaxies can be. As telescopes improve and survey strategies optimize for detecting extended faint structures, new populations of ultra-diffuse and possibly hyper-diffuse galaxies will emerge. These discoveries will reveal the full diversity of galaxy properties and test the limits of how inefficiently dark matter halos can convert gas into stars. The existence of ultra-diffuse galaxies also affects galaxy counts and mass estimates in clusters. Traditional surveys that focus on bright, compact galaxies miss UDGs entirely, undercounting the total galaxy population by significant factors. When UDGs are included, cluster galaxy populations increase by 20 to 50%. This affects estimates of cluster masses, galaxy luminosity functions, and the efficiency of star formation across cosmic time. Ignoring UDGs creates systematic biases in our understanding of how matter is distributed in the universe. When you observe an ultra-diffuse galaxy, you are seeing failure, not the violent failure of a merger that creates an elliptical, but the quiet failure of a system that could not or would not form stars. It assembled a massive dark matter halo, accreted gas, began the star formation process, and then stopped. Perhaps feedback was too strong. Perhaps the gas was stripped away before stars could form. Perhaps some physical process we do not understand prevented efficient star formation. The result is a cosmic ghost, a dark matter skeleton with just enough flesh to mark its presence. Stretched across volumes that should contain billions of suns but instead hold only millions. These ghosts are numerous. They surround every massive galaxy and every cluster. They float through voids. They are the shadows of what galaxies could have been if star formation had not failed. And they remind us that the universe is filled not just with brilliant stellar systems, but with dark failures. Objects that came close to being galaxies but fell short, leaving behind only faint traces to mark where they almost existed. There are galaxies in the universe that contain no stars. They are clouds of hydrogen gas and dark matter floating through space, completely invisible in optical telescopes, detectable only through radio emissions from their neutral hydrogen or through gravitational effects on their surroundings. They are called dark galaxies, and their existence challenges the fundamental definition of what a galaxy is. If a galaxy contains no stars, is it still a galaxy? Or is it something else? A failed structure that never completed its transformation from primordial gas cloud to stellar system. The prediction of dark galaxies dates back to the 1980s when cosmological simulations showed that not all dark matter halos should successfully form stars. Some halos, particularly those with masses below certain thresholds, might accrete gas but never trigger star formation. The gas would remain in atomic or molecular form, rotating within the dark matter potential well, but never collapsing to densities high enough to ignite fusion. These systems would be completely dark, except for the emission lines from their gas and the gravitational effects from their dark matter. Detecting dark galaxies is extraordinarily difficult because they produce no light. You cannot photograph them. You cannot see them through optical telescopes. The only way to find them is to search for their radio emissions at the 21-centimeter wavelength where neutral hydrogen emits, or to look for gravitational lensing effects where their mass bends light from background sources. Both methods require enormous sensitivity and extensive surveys to cover sufficient volumes of space. In 2005, astronomers using the Arecibo Observatory claimed the first detection of a dark galaxy, a cloud of neutral hydrogen designated Virgohi 21, located in the Virgo cluster. The object contained roughly 100 million solar masses of hydrogen gas, but showed no optical counterpart. No stars were visible at the position of the hydrogen cloud. The discovery was controversial because alternative explanations existed. The hydrogen cloud might be tidal debris stripped from a normal galaxy during an interaction, gas that had been removed but not yet dispersed. Or it might be an extremely low surface brightness dwarf galaxy where stars exist but are too faint to detect with available instruments. Follow-up observations with more sensitive optical telescopes eventually detected a faint stellar population associated with Virgohi 21. The system was not completely dark, but was an ultra-faint dwarf galaxy with an extremely high gas-to-stellar mass ratio. This pattern repeated with other dark galaxy candidates. When observers obtained sufficiently deep images, they found faint stars. The dark galaxies were not truly starless, but were gas-rich systems with extremely inefficient star formation. However, the failure to find completely starless dark galaxies does not mean they do not exist. Current detection limits only reveal dark galaxies bright enough in neutral hydrogen emission to be detected by existing radio telescopes and in regions of sky that have been surveyed. Fainter dark galaxies or systems in unsurveyed regions would remain undetected. Theoretical models predict that truly starless dark galaxies should exist in cosmic voids and in the outskirts of galaxy clusters, where environmental conditions prevent star formation while allowing gas retention. The processes that could create starless dark galaxies involve feedback and environmental effects operating at extreme levels. Reionization heating from the first stars would raise the temperature of intergalactic gas, preventing it from cooling and collapsing into low-mass halos. Halos below approximately 1 million solar masses might never cool sufficiently to form stars, remaining as gas-filled dark matter structures. Photoionization from nearby quasars or intense ultraviolet sources could further suppress star formation by heating and ionizing the gas. Ram pressure from moving through the intergalactic medium could remove the ability of gas to collapse, even if the halo retains the gas itself. Dark galaxies represent one extreme of galaxy properties. systems that are almost entirely dark. Starburst galaxies represent the opposite extreme, systems forming stars so intensely that they outshine everything else in their environments. Starburst galaxies convert gas into stars at rates exceeding 100 solar masses per year, hundreds of times faster than the Milky Way's current rate of approximately 2 solar masses per year. They are cosmic bonfires consuming their fuel in brief explosive episodes that last only tens of millions of years. The infrared luminosities of the most extreme starbursts exceed 1 trillion solar luminosities, making them among the most luminous objects in the universe. These ultraluminous infrared galaxies, or ULIRGs, emit more than 99% of their energy in infrared wavelengths, produced by dust grains heated by intense ultraviolet radiation from young massive stars. The dust absorbs the ultraviolet light and re-emits it as thermal infrared radiation, creating objects that are faint in optical wavelengths but blazingly bright in the infrared. Starbursts are almost always triggered by galaxy mergers. When two gas-rich galaxies collide, the gravitational torques funnel gas toward the centers of both systems. The gas densities increase dramatically, exceeding the thresholds required for gravitational collapse. The entire gas reservoir can collapse nearly simultaneously, forming stars across the merger remnant at extraordinary rates. The merger of two Milky Way-sized spiral galaxies can trigger starbursts, forming over 10 billion solar masses of stars within 100 million years. The antenna galaxies provide a spectacular example of merger-triggered starburst activity. These two colliding spirals are experiencing intense star formation in the overlap region where their disks interact. Observations with the Hubble Space Telescope reveal over 1,000 young star clusters forming in this collision zone, each containing millions of stars packed into regions only tens of light-years across. These superstar clusters are the modern analogs of ancient globular clusters, forming through the same processes but in gas-rich merger environments rather than in the early universe. The extreme ultraviolet radiation from starburst galaxies ionizes the surrounding gas, creating enormous ionized regions hundreds or thousands of light-years across. The Lyman alpha emission from this ionized hydrogen makes starbursts visible across vast cosmic distances. High redshift starbursts can be detected when the universe was only 1 to 2 billion years old, revealing that intense star formation was common in the early universe when galaxy merger rates were higher and gas supplies were more abundant. But starburst activity cannot be sustained indefinitely. The intense star formation consumes the available gas supply within tens to hundreds of millions of years. The massive stars formed during the burst have lifetimes of only a few million years before exploding as supernovae. These supernovae inject enormous amounts of energy into the surrounding gas, driving winds that can expel remaining gas from the galaxy entirely. The combined effect of fuel exhaustion and supernova feedback causes the starburst to self-terminate, leaving behind a post-starburst galaxy with a young, stellar population but no ongoing star formation. Post-starburst galaxies, also called E+A galaxies because their spectra show strong Balmer absorption lines from A-type stars superimposed on early-type galaxy continua, represent the immediate aftermath of starburst episodes. These systems have stellar populations, dominated by stars with ages of a few hundred million to 1 billion years, young enough to still contain luminous A-type stars, but old enough that the most massive stars have already died. Post-starburst galaxies are in transition from active star-forming systems to quiescent red galaxies. They represent a critical phase of galaxy evolution where star formation has just recently ceased. The winds driven by starburst activity can reach velocities exceeding 1,000 kilometers per second, fast enough to escape even from massive galaxy potential wells. These outflows carry metal-enriched gas into the circumgalactic medium and intergalactic medium, polluting vast regions with heavy elements created in the starburst stars. This pollution affects future star formation in the galaxy's surroundings and contributes to the metal enrichment of the intergalactic medium observed in absorption line systems along quasar sightlines. Some starburst galaxies show evidence of obscured active galactic nuclei at their centers, supermassive black holes actively accreting matter and emitting enormous amounts of energy. The connection between starburst activity and AGN activity suggests they are linked through the same merger processes. As gas funnels toward the galactic center during a merger, it both triggers star formation throughout the system and feeds the central supermassive black hole. The black hole grows through accretion while the galaxy undergoes a starburst, creating a phase where both processes occur simultaneously. The luminosity of the AGN can eventually exceed the starburst luminosity as the black hole accretion rate increases. The AGN then drives powerful winds and jets that heat the surrounding gas and prevent further star formation, effectively shutting down both the starburst and the AGN's own fuel supply. This AGN feedback is thought to be the primary mechanism regulating star formation in massive galaxies and preventing them from converting all their gas into stars. The ARP-220 galaxy system illustrates this evolutionary sequence. This ultraluminous infrared galaxy is experiencing both an intense starburst and AGN activity following the merger of two gas-rich spirals. X-ray observations reveal a luminous AGN at the system's center, while infrared observations show widespread star formation throughout the merger remnant. The system will likely evolve into a massive elliptical galaxy once the gas is exhausted and the activity subsides. Starburst galaxies at high redshift in the early universe show different properties than local starbursts. Submillimeter galaxies detected through their thermal dust emission at submillimeter wavelengths are forming stars at rates exceeding 1,000 solar masses per year, when the universe was only 2 to 3 billion years old. These systems are building stellar masses comparable to the most massive galaxies in the present-day universe within a few hundred million years. They represent the formation of today's most massive ellipticals through extraordinarily rapid star formation in the early universe. The relationship between dark galaxies and starburst galaxies is one of cosmic irony. Dark galaxies are systems that have gas but form essentially no stars. Starbursts are systems forming stars so rapidly that they exhaust their gas in cosmic eye blinks. Both represent failure modes of normal star formation. Dark galaxies fail to start forming stars efficiently. Starbursts form stars too efficiently and destroy their ability to continue. Normal galaxies like the Milky Way maintain moderate star formation rates for billions of years, balancing gas consumption with gas accretion to sustain stellar population growth. Dark galaxies and starbursts represent the extremes where this balance breaks down completely. The existence of both types reveals that galaxy formation is not a smooth, deterministic process, but a chaotic stochastic one where outcomes depend sensitively on initial conditions, environmental factors, and random merger histories. Some systems end up gas-rich and star-poor. Others become star factories that consume everything. Most land somewhere between these extremes, forming stars at moderate rates that allow extended evolutionary timescales. But the extremes are not rare. Dark galaxy candidates number in the hundreds. Starburst galaxies are detected by the thousands in deep infrared surveys. The extremes are common enough to be significant populations, not just rare outliers. Understanding why some halos become dark galaxies, while others become starbursts, requires detailed knowledge of the physics of gas cooling, star formation, and feedback. Gas must cool to collapse. Cooling rates depend on metallicity, density, and temperature. Low metallicity gas cools poorly because it lacks the metal atoms that radiate efficiently. High metallicity gas cools rapidly, promoting star formation. Dark galaxies might be low metallicity systems where cooling is suppressed. Starbursts might be metal-enriched systems where efficient cooling drives runaway collapse. Feedback processes complicate this picture further. Supernovae inject energy that heats gas and prevents cooling. But if star formation occurs in concentrated regions, the feedback can drive winds that remove gas entirely rather than redistributing it. The geometry of star formation determines whether feedback suppresses or enhances further activity. Distributed star formation leads to self-regulation. Concentrated star formation leads to blowout and termination. Dark galaxies and starbursts might represent systems where feedback operated differently, one suppressing star formation before it started, the other failing to suppress until all fuel was consumed. The future of dark galaxies and starbursts is convergence. Dark galaxies can potentially trigger star formation if they accrete metal-enriched gas from their surroundings, or if they experience environmental compression that increases their gas densities. They could transition from dark to dwarf, irregular, beginning modest star formation that gradually converts their gas reservoirs into stars over billions of years. Starbursts will inevitably fade into red post-starburst systems that gradually redden further as their stellar populations age. Within a few billion years, a starburst becomes indistinguishable from an old elliptical or lenticular galaxy, its violent past erased from its appearance though preserved in its stellar populations. When you observe a dark galaxy or a starburst, you are witnessing the extremes of cosmic possibility. Dark galaxies show how close the universe came to creating a galaxy but failed at the final step, assembling all the ingredients but never igniting the fusion reactions that would make it luminous. Starbursts show what happens when every constraint fails simultaneously, when all the gas collapses at once in an orgy of star formation that cannot sustain itself. Both are warnings. Dark galaxies warn that assembly does not guarantee activation. Starbursts warn that activation without regulation leads to rapid exhaustion. And between these warnings lies the narrow path that normal galaxies must walk to survive for cosmic timescales. You now understand the lie. The galaxy types you were taught do not exist as stable categories. Spirals are not spiraling. Ellipticals are graveyards. Irregulars follow hidden rules. Lenticulars are transition corpses. Rings should collapse. Dwarves are predators. Ultra-diffuse galaxies are ghosts. Dark galaxies have no stars. Starbursts consume themselves. Every classification is a simplification so extreme that it erases the actual physics, the violence, the failure, the temporary equilibrium masquerading as permanent structure. And the classification nightmare does not end with the types we have discussed. It extends into exotic categories that shatter what remains of our illusion that we understand galactic structure. Polar ring galaxies host gas and stars, orbiting perpendicular to their main bodies, creating structures that look like cosmic gyroscopes. Shell galaxies show concentric arcs of stars surrounding their cores, fossil tidal streams from cannibalized satellites arranged in geometric patterns. Jellyfish galaxies trail tentacles of stripped gas and stars as they move through intracluster medium, their disks being torn away in real time. Hogue-type objects display perfect rings surrounding isolated nuclei through mechanisms we cannot fully explain. Tadpole galaxies extend single massive tidal tails, stretching hundreds of thousands of light-years behind disturbed cores, captured mid-disruption by gravitational encounters. Then there are the active galaxies, systems where supermassive black holes dominate the energy output. Seyfert galaxies host accreting black holes that outshine their stellar populations in certain wavelengths. Radio galaxies launch jets of relativistic particles that extend for millions of light-years, visible primarily in radio wavelengths, while appearing unremarkable optically. Blazars are radio galaxies oriented so their jets point directly at Earth, creating variable sources that can change brightness by factors of 10 within days. Quasars are the most luminous active galaxies, supermassive black holes accreting at extreme rates and outshining entire galaxy clusters, despite being powered by regions smaller than our solar system. The morphology-density relation reveals that galaxy types are not randomly distributed, but depend strongly on environment. Elliptical and lenticular galaxies dominate dense galaxy clusters. Spiral and irregular galaxies dominate the field and low-density groups. This environmental dependence proves that galaxy types are not primordial properties, but products of evolutionary processes shaped by surroundings. A spiral galaxy that forms in isolation evolves differently than one that forms in a cluster. The classification reflects where the galaxy lives as much as what it inherently is. The morphology-color relation shows that red galaxies are preferentially elliptical, while blue galaxies are preferentially spiral. But this correlation is not perfect. Blue ellipticals exist, systems that somehow maintain star formation despite lacking gas-rich disks. Red spirals exist, systems that retain spiral structure despite having ceased star formation. These transitional objects populate the green valley between the red sequence and the blue cloud in color magnitude diagrams, representing galaxies caught between active and quiescent states. The Green Valley is not sparsely populated but contains significant numbers of galaxies undergoing transformation, showing that the boundaries between types are populated regions rather than sharp divisions. Citizen science projects like Galaxy Zoo have classified millions of galaxy images using human pattern recognition, revealing that approximately 20 to 30% of observed galaxies cannot be confidently assigned to any Hubble type. These peculiar galaxies show asymmetries, disturbances, multiple nuclei, or morphological features that defy categorization. They are not rare oddballs, but a substantial minority of the total population. If nearly 1/3 of galaxies do not fit the classification system, the system is fundamentally inadequate for describing the diversity of cosmic structures. Machine learning algorithms trained to classify galaxy morphologies struggle with the same problems humans face. Neural networks can learn to distinguish spirals from ellipticals with high accuracy when presented with clear examples, but they perform poorly on edge cases, transitional objects, and highly disturbed systems. The algorithms reveal that the boundaries between galaxy types are fuzzy and context-dependent rather than sharp and absolute. Classification is not discovering natural categories but imposing human organizational schemes on continuous distributions of properties. The high redshift universe contains galaxy morphologies with no local analogs. Clumpy, irregular galaxies dominate at redshifts greater than 2, when the universe was less than 3 billion years old. These systems show multiple bright knots of star formation embedded in extended disks, creating appearances unlike any nearby galaxy. They are not classical irregulars or spirals or ellipticals, but represent a different mode of galaxy structure that was common in the early universe but has disappeared in the present day. Our classification system developed for local galaxies is useless for describing these early systems. Chain galaxies appear as elongated structures with multiple bright knots arranged in linear configurations. They might be merger remnants or systems forming through fragmentation of gas-rich filaments. Tadpole galaxies extend single massive tidal tails stretching hundreds of thousands of light-years behind disturbed cores, captured mid-disruption by gravitational encounters. Collisional ring galaxies show expanding rings of star formation triggered by head-on impacts. Luminous infrared galaxies shine primarily in infrared wavelengths due to obscuring dust heated by intense star formation or AGN activity. Each category represents a different physical process, a different formation mechanism, a different evolutionary state. The diversity is not being captured by traditional morphological classification. The realization that galaxy types are not natural kinds but human constructs has profound implications. We are not discovering the universe's organizational structure. We are imposing our own structure on data that resists categorization. The universe does not care about our classification schemes. Galaxies form through physical processes governed by gravity, gas dynamics, star formation, and feedback. These processes create a continuous range of outcomes depending on mass, angular momentum, merger history, and environment. Our categories carve this continuum into discrete boxes for convenience, but the boxes are artificial. Future classification systems will likely abandon morphology entirely in favor of physical properties. Instead of asking what a galaxy looks like, we should ask what its mass is, what its star formation rate is, what its gas content is, what its merger history is, what its environment is. These physical properties directly reflect the processes shaping the galaxy and predict its future evolution. Morphology is a consequence, not a cause. Two galaxies with identical physical properties will evolve similarly, even if they currently have different visual appearances due to projection effects or transient features. The James Webb Space Telescope is discovering galaxies at redshifts greater than 10, systems forming less than 500 million years after the Big Bang. These galaxies are small, clumpy, and extremely different from modern systems. They are assembling from smaller fragments through ongoing mergers. They have not yet settled into stable configurations. Their morphologies change on timescales of tens of millions of years, as mergers progress and star formation episodes begin and end. Classifying such dynamic objects by their instantaneous appearance is meaningless. They are process incarnate, not stable structures. The ultimate galaxy classification would track every galaxy's complete history from formation through evolution to eventual fate. It would record every merger event, every star formation episode, Every interaction with neighbors, every accretion of gas, every loss of gas through feedback or stripping. The classification would be a complete narrative rather than a snapshot label. But such classification is impossible with current observational capabilities. We see galaxies at single moments in their histories, and must infer their pasts and futures from that limited information. What we call galaxy types are therefore shadows of true physical reality. They are projections of complex four-dimensional histories onto two-dimensional images at single instants in cosmic time. They capture some information about galaxy properties but lose most of the relevant physics. They create illusions of understanding while concealing ignorance. And they trap us in frameworks that prevent us from asking the right questions about how cosmic structures actually form and evolve. The universe contains approximately 200 billion galaxies within the observable volume. Each one is unique. Each has experienced its own sequence of events shaped by local conditions, random encounters, and stochastic processes. No two galaxies are identical. Classification schemes that group them into handfuls of types are not revealing fundamental truths about cosmic organization. They are applying crude labels to manage cognitive overload when confronted with overwhelming diversity. When you look at a galaxy and think you know what type it is, you are not demonstrating knowledge. You are demonstrating the human mind's desperate need to organize complexity into manageable categories even when those categories do violence to reality. The spiral you see is not spiraling. The elliptical is not a simple ellipsoid. The irregular is not chaotic. The dwarf is not harmless. The classifications are lies we tell ourselves to avoid confronting the terrifying truth that the universe is far more complex, far more violent, and far more resistant to human comprehension than we want to believe. The types of galaxies you never knew existed are not exotic exceptions. They are the majority. The comfortable categories you learned are the exceptions, idealized cases that barely exist in nature. Reality is rings that should collapse, dwarfs that devour giants. Ghosts spread across impossible volumes, monsters that consume themselves. Dark structures with no stars. And between all these extremes are infinite gradations, transitional objects, hybrid systems, and structures so bizarre that we have not yet invented names for them. The classification nightmare never ends because the universe never stops producing new configurations, new failure modes, new ways for gravity to organize matter that defy our expectations and shatter our models. For every galaxy type we identify and think we understand, 10 more await discovery at the edges of our detection capabilities or in the dark spaces between categories where observations cannot yet reach. The catalog will never be complete. The taxonomy will never be adequate. The understanding will never be total. You are living inside a galaxy classified as a barred spiral. But that classification tells you almost nothing about what the Milky Way actually is, how it formed, what it is doing, or what will happen to it. The bar is a temporary structure that will dissolve within a few billion years. The spiral arms are density waves, not material structures. The halo is built from consumed dwarfs. The disk is being perturbed by ongoing accretion. The classification barred spiral conceals all of this, reducing billions of years of violent history and ongoing evolution to two words that mean almost nothing. If you want to understand galaxies, forget the types. Focus on the physics, learn the processes, study the violence. Accept the complexity. Abandon the illusion that we can organize cosmic structure into neat categories that make sense to human minds. The universe does not owe us comprehensibility. It operates according to its own principles, creating structures that emerge from the interplay of gravity, gas, stars, and dark matter, without consulting our classification schemes or caring whether we can understand the results. The types of galaxies you never knew existed are the majority of galaxies that exist. Everything else is the lie we tell ourselves to sleep at night. To pretend we understand the cosmos, to maintain the fiction that we have mapped and categorized and comprehended the structures hanging in the void above our heads. We have not. We have barely begun, and what we will discover as our instruments improve and our theories evolve will make everything we currently know look like the first crude sketches of explorers who thought they had mapped a continent after visiting one beach. If this terrified you, if this shattered your comfortable understanding of galactic structure, then it has done its job. Hit that like button, subscribe to this channel, because the nightmare is just beginning. And there are far more cosmic horrors waiting to be revealed than you ever imagined possible.